We are often told that the universe is out there, a vast and distant place that we merely observe from the safety of our small blue world. But this separation is an illusion. We look at the night sky and see a void punctuated by distant lights, believing ourselves to be distinct from the theater we are watching. Yet the physical reality is far more intimate and far more strange. The hydrogen in the water you drink is 13.8 billion years old, a relic from the first moments of existence. And the gold in the jewelry you might wear required the collision of dead stars to forge its heavy nucleus. This is not a story of how small we are in the face of the void, but rather the story of how the void came together over billions of years to become you. We search the galaxy for extraterrestrial life, scanning the radio waves for a signal from the unknown. Yet we often forget that we are the strangest things in the galaxy, living stardust that has learned to name itself. To understand the biological map that leads from the center of a star to the center of your cells, we must return to a time before biology was possible, a time when the universe was a simple, silent place. 380,000 years after the initial expansion event we call the Big Bang, the cosmos was not filled with galaxies or planets, but was instead a uniform fog of neutral hydrogen and helium gas. There were no solids, no liquids, and certainly no oxygen to breathe. Only a dark, expanding sea of the simplest elements in existence. This era, known to cosmologists as the Cosmic Dark Ages, was a time of profound waiting, where the universe consisted almost entirely of potential, a vast canvas of darkness holding the raw material for everything that would eventually come to be. Every molecule of water currently residing in your body contains hydrogen atoms that were born in this exact moment of cosmic history.
They are the elders of your biological structure, witnesses to a time before light, and they have traveled through the eons to become part of the fluid that sustains your life. But hydrogen alone cannot build a bone. Told us the universe needed a furnace, and so slowly, inevitably, gravity began to do its work. In the density fluctuations of that primordial fog, gravity began to pull the gas together, gently at first, and then with increasing insistence, drawing the hydrogen atoms into massive swirling clouds. As these clouds collapsed under their own immense weight, the pressure at their centers began to rise, heating the gas until the atoms were stripping themselves of their electrons, creating a plasma so hot and so dense that the fundamental rules of chemistry were rewritten. This was not a violent collapse in the traditional sense, but a gathering, a great coalescing of material that would eventually ignite the first generation of stars, known as population 3 stars, ending the Dark Ages and illuminating the void with the first light of creation. Deep within the hearts of these newborn stars, a process known as stellar nucleosynthesis began, a mechanism that serves as the engine of the universe and the origin of your physical form. The core of a star is a region of unimaginable extremes, where the temperature soars to 15 million Kelvin and the pressure is sufficient to crush atoms together, overcoming the natural electromagnetic repulsion that keeps atomic nuclei apart. In this crushing environment, the star begins the proton-proton chain reaction, a a sequence of nuclear fusion events that transforms hydrogen into helium.
It is a process of elegant efficiency where 4 hydrogen protons are squeezed until they fuse, releasing a positron and a neutrino, and eventually forming a helium-4 nucleus. In doing so, a tiny fraction of the mass of the protons is lost, converted directly into energy, according to Einstein's famous equivalence principle, releasing a photon of high-energy gamma radiation. This photon, born in the crushing dark of the core, begins a long and tortuous journey toward the surface, bouncing between particles in a random walk that can take tens of thousands of years, losing energy with every collision, until it finally emerges from the surface of the star as visible light. This light, which we perceive as sunshine, is not merely energy. It is the byproduct of the star's digestion, the radiant exhaust of a machine that is transmuting the simplest element into the second simplest. When you feel the warmth of the sun on your skin, you are feeling the echo of a nuclear fusion event that occurred deep within the solar core, a transfer of energy that will eventually drive the photosynthesis of plants, creating the chemical bonds that you will consume as food. The star is, in a very literal sense, pre-digesting the energy of the universe, packaging it into a format that biology can eventually utilize, creating a bridge between the nuclear physics of the core and the metabolic physics of the cell. For the majority of a star's life, it remains in this stable state, known as the main sequence, balancing the inward pull of gravity with the outward pressure of fusion energy, maintaining a hydrostatic equilibrium that can last for billions of years. This cosmic patience is necessary for life, providing a stable environment where planets can form and evolution can unfold. But hydrogen fusion alone is a dead end for complexity. A universe filled only with hydrogen and helium is a sterile place, devoid of the chemistry required for water, for rock, or for blood. For the universe to create the carbon that forms the backbone of your DNA, the star must age and it must change. As the star exhausts the hydrogen fuel in its core, the delicate balance of hydrostatic equilibrium is broken, causing the core to contract and heat up further, while the outer layers of the star expand and cool, transforming the star into a red giant. This is not a dying gasp, but a blooming, a necessary metamorphosis that unlocks a new tier of nuclear alchemy, capable of forging heavier elements. As the core temperature rises to 100 million Kelvin, the star begins to fuse helium nuclei together, a process that is statistically improbable and deeply complex, known as the triple alpha process. Carbon, the element that allows for the complexity of life due to its unique ability to bond with up to 4 other atoms simultaneously, is incredibly difficult to manufacture in the natural world. It requires 3 helium-4 nuclei, also known as alpha particles, to collide at almost exactly the same moment, a synchronized event that defies the odds of random motion. 2 helium nuclei collide to form beryllium-8, an isotope so unstable that it decays back into helium in a fraction of a femtosecond, meaning that a 3rd helium nucleus must strike this fleeting beryllium atom before it falls apart. It is a window of opportunity so narrow that it seems almost designed to fail, yet in the dense, hot cores of red giants, it happens often enough to enrich the universe with carbon. This carbon is the architectural scaffolding of all known life, the social butterfly of the periodic table that allows for the formation of proteins, lipids, and carbohydrates. Every carbon atom in every cell of your body was forged in this specific precarious manner, cooked in the belly of a dying giant that lived and died long before our sun was born. The star, in its swelling redness, has created the possibility of complexity, transforming the sterile gas of the early universe into the building blocks of biology. Yet these elements remain trapped behind a wall of plasma, locked deep within the gravitational well of their creator. As the star continues to evolve, the core begins to stratify, resembling the layers of an onion, with each layer dominated by a different fusion process and a different element. In the most massive stars, those far larger than our Sun, the pressure and temperature continue to climb, initiating the carbon-nitrogen-oxygen cycle, or CNO cycle, which acts as a catalyst for hydrogen fusion, while simultaneously producing nitrogen and oxygen as byproducts. This is the moment where the breath of the cosmos is forged, creating the oxygen that will one day fill the lungs of creatures on a distant rocky world. The oxygen in the air you breathe is a stellar exhaust product, a chemical ash left over from the burning of carbon and helium in the high-pressure crucible of a supergiant star. This connection goes deeper than simple respiration. The very mechanism that your cells use to generate energy, the mitochondria, relies on oxygen to burn sugar, a process that is essentially a slow, controlled combustion. The fire that burns in your cells is a chemical echo of the nuclear fire that burns in the star, a biological repurposing of the energy release mechanisms that govern the cosmos. Inside the star, the layers continue to build, with hydrogen fusing on the outside, helium fusing beneath it, followed by shells of carbon, neon, and oxygen, creating a geode of potential life held together by gravity. Despite the unimaginable heat and the ferocity of the reactions, the process is silent, a rhythmic, billions-year-long heartbeat of contraction and ignition, driving the synthesis of heavier and heavier elements.
The star is meticulously assembling the periodic table, moving from the simplicity of gas to the complexity of solids, creating the silicon that will form the rocks of Earth and the calcium that will form your skeleton. But this process of fusion, this climbing of the atomic ladder, eventually hits a wall, a barrier that no star can cross without paying the ultimate price. As the star begins to fuse silicon into iron, it encounters a fundamental limit of nuclear physics known as the iron peak. For all lighter elements, fusing them together releases energy, creating the outward pressure that supports the star against gravity. But fusing iron is different. Iron 56 has one of the most tightly bound nuclei in existence, meaning that fusing it into something heavier consumes energy rather than creating it. When the star's core transforms into iron, the engine stops because the fuel has become a fire retardant, absorbing the heat of the core and draining the star of the energy it needs to support its own weight. This accumulation of iron is often described as the death of the star, but in the context of our biological map, it is better understood as the iron sacrifice. The iron that courses through your veins, bound to the hemoglobin molecules that carry oxygen to your brain, was forged in these final, desperate moments of a star's life. Without this iron, complex life as we know it would be impossible, for we would lack the mechanism to transport oxygen efficiently throughout a multicellular body. Furthermore, the iron that sank to the center of the Earth to create the molten core is responsible for generating the planet's magnetic field, the invisible shield that protects our atmosphere from the stripping winds of the sun. The death of the star's energy generation mechanism is the birth of our protection, a trade-off where the star sacrifices its stability to create the heavy metal that will anchor a future world.
The core, now a massive sphere of iron ash, grows heavy and inert, no longer producing the radiation pressure required to hold back the crushing weight of the star's outer layers.
The delicate balance that held the star up for millions of years is broken, and gravity, which has been waiting patiently since the first clouds of hydrogen began to gather, finally wins the war. The star begins to collapse, not because it failed, but because it finished its work, condensing the fruits of its labor into a tight, dense package, readying the elements for delivery into the cosmos. The theoretical models suggest a potential instability of catastrophic proportions, where the core collapses in a fraction of a second, moving from the size of Earth to the size of a city, reaching densities that defy comprehension. This collapse is the prelude to the greatest release of energy the universe can produce, a mechanism that will scatter the carbon, the oxygen, and the iron across the galaxy, sowing the seeds for future solar systems. But before the explosion, there is a moment of silence, a final intake of breath, where the star hangs suspended between existence and oblivion, holding within it all the ingredients necessary for you. The universe has spent billions of years preparing this mixture, carefully fusing proton to proton, helium to helium, building the complex nuclei that will eventually encode the information of life. We are not merely inhabitants of the universe. We are the universe's way of preserving this complexity, walking, breathing artifacts of a nucleosynthesis process that began in the dark and ended in iron. The story of your body is the story of this forge, a narrative written in the language of isotopes and binding energy, waiting for the shockwave that will set it free. The collapse of the iron core occurs in less than a quarter of a second, a time frame so infinitesimal that the outer layers of the star, still suspended by their own immense inertia, are momentarily
unaware that the floor has fallen out from beneath them. As the core compresses from a diameter of several thousand kilometers down to a mere 20, the protons and electrons are crushed together with such violence that they merge to form neutrons, creating a substance of unimaginable density where a single teaspoon would weigh more than a mountain range. This sudden densification reaches a hard limit, a wall of nuclear resistance known as neutron degeneracy pressure, which halts the collapse with an abruptness that defies the laws of macroscopic physics, transforming the inward rushing matter into a rigid sphere that acts as an impenetrable anvil. The infalling outer layers, rushing inward at speeds approaching a significant fraction of the speed of light, strike this neutron anvil and bounce, reversing their trajectory in a colossal rebound that generates a shockwave of kinetic energy capable of outshining an entire galaxy. This is the moment of the supernova, not merely a destructive explosion, but the primary distribution mechanism of the universe, a cosmic sowing event that propels the carbon, oxygen, and nitrogen synthesized over billions of years out into the vast sterile dark of the interstellar medium. Within the intense heat and pressure of this shockwave, a new form of alchemy takes place, a phenomenon physicists call the R process, or rapid neutron capture process, where atomic nuclei are bombarded with neutrons so quickly that they do not have time to decay before capturing another. This rapid bombardment forces the nuclei to swell, climbing the periodic table far beyond iron, forging the heavier elements that standard fusion could never create, constructing the isotopes of zinc that now reside in your immune system and the iodine essential for the function of your thyroid. It is here, in the violent, blinding expansion of the dying star,
that the universe finally creates the complex chemical palette required for biological life, transforming the
death of a single celestial object into the potential for a billion living things. The shockwave travels outward for millennia, carrying these precious materials across the galaxy, expanding into a nebula of glowing gas that drifts silently through the vacuum, a colorful, intricate tapestry of filaments and knots that serves as a monument to the star that once was. These remnants, such as the Veil Nebula or the Crab Nebula, are often viewed as scars on the face of the galaxy. Yet, in the context of our biological origins, they are better understood as fertile soil, vast clouds of enriched dust waiting for the gravitational conditions necessary to begin the cycle anew. The atoms that currently compose your hand, the calcium in your fingernails, and the phosphorus in your DNA, once drifted in such a cloud, suspended in the cold silence of space for eons, moving with the gentle currents of the galactic rotation. There is no urgency in this process, only the slow, inevitable drift of matter, a patience that spans geological epochs, allowing the enriched gas to mix with the primordial hydrogen of the cosmos, diluting the heavy elements into a mixture capable of forming stable planetary systems. However, the standard supernova, for all its power, cannot account for the abundance of the heaviest elements found on Earth, specifically the gold in your jewelry or the uranium that heats the planetary core. To forge these ultra-heavy nuclei, the universe requires a crucible of even greater density, a mechanism that involves the remnants of the stars that have already died. Occasionally, when massive stars exist in binary systems, they leave behind two neutron stars, the ultra-dense cores that survived the initial supernova explosions, now locked in a gravitational embrace, spiraling inward toward one another over billions of years. As they draw closer, shedding orbital energy in the form of gravitational waves, ripples in the very fabric of spacetime, they accelerate to velocities approaching the speed of light, their immense gravity distorting the space around them until they finally collide. This collision, known as a kilonova, is a rare and cataclysmic event, a brief moment where the density and temperature spike high enough to run the R process to its absolute limit, producing vast quantities of the heaviest stable elements in the periodic table. It is estimated that a single neutron star collision can produce a mass of gold equal to 10 times the mass of the Earth, casting it out into the universe as a fine mist of atomic vapor. This means that the gold ring you might wear, or the platinum used in medical devices, is not merely a rare metal dug from the ground, but the direct artifact of a collision between two dead stars that occurred billions of years before our solar system even existed. These atoms traveled across the void, riding the shockwaves of the collision, eventually mingling with the pre-solar nebula, the great cloud of gas and dust that would one day collapse to form our sun and its planets. The gathering of this material marks the transition from the chaotic dispersion of the galaxy to the ordered formation of a home, a process governed by the conservation of angular momentum. As the great cloud of enriched gas and dust, the solar nebula, begins to collapse under its own gravity, perhaps triggered by the shockwave of a nearby supernova, it does not fall directly inward, but begins to spin, flattening out into a vast rotating disk.
In the center, the pressure mounts, the temperature rises, and the protostar that will become our sun begins to glow, igniting the nuclear fires that will sustain it for 10 billion years. But out in the disk, in the cold reaches where the light is dim, the heavy elements begin to condense, transitioning from gas to solid grains of dust, microscopic particles of iron, silicates, and ice that act as the seeds of worlds.
This is the era of accretion, a period of gentle collisions where dust grains stick together to form pebbles. Pebbles merge to form boulders, and boulders coalesce into planetesimals, kilometer-sized rocks that exert their own gravitational pull. It is a process of sorting, a cosmic filtration system where the heat of the young sun pushes the volatile gases outward, creating the gas giants of Jupiter and Saturn, while the heavy refractory materials, the iron, the magnesium, the silicon, remain in the inner system to build the rocky planets. The Earth forms in this inner zone, a hot, molten sphere accumulating mass from the constant bombardment of planetesimals, a chaotic and violent birth that slowly builds the platform upon which life will eventually stand. Yet this early Earth was a dry and hostile world, rich in rock and metal, but lacking the volatile compounds necessary for biology, specifically the water that makes up 70% of your body, and the carbon-based molecules that form the machinery of your cells. The delivery of these essential ingredients required a second wave of bombardment, a period known as the Late Heavy Bombardment, where the gravitational migration of the giant planets disturbed the orbits of the comets and asteroids in the outer solar system, sending them plunging inward toward the sun. These icy bodies, remnants of the solar system's formation that had been stored in the deep freeze of the Kuiper Belt and the Oort cloud, acted as cosmic tankers, carrying vast reservoirs of water and frozen organic compounds across the interplanetary void. When these comets struck the young Earth, they vaporized upon impact, releasing their cargo into the atmosphere, creating a thick blanket of steam that would eventually condense and fall as rain, a deluge that lasted for millions of years. This ancient rain, filling the low-lying basins of the crust, formed the first oceans, a global solvent in which the chemistry of life could begin to experiment. It is a profound realization that the water you drink today, the fluid that courses through your blood and fills the interior of your cells, is extraterrestrial in origin, delivered to this planet by the bombardment of ice from the edge of the solar system. We are, in a very literal sense, bodies of water that have learned to walk on land, carrying our own internal oceans as a portable environment that mimics the salinity and conditions of the primordial sea. The stage was thus set, not by a single act of creation, but by a cascading series of astrophysical events, a chain of causality linking the fusion in the core of a dying star to the condensation of water on a cooling rock. The atmosphere, initially a toxic brew of carbon dioxide, nitrogen, and methane, began to settle, shielded from the stripping winds of the sun by the magnetic field generated by the iron core, that same iron that was forged in the final moments of the stellar collapse. The surface cooled, forming a crust of silicate rock, enriched with the radioactive isotopes of uranium and thorium that provide the internal heat necessary to drive plate tectonics, a geological recycling process
that regulates the planet's temperature and keeps the carbon cycle in motion. In this quiet, watery cradle, the atoms that had been forged in the hearts of stars and scattered by supernovas began to do something unprecedented. They began to organize. The distinction between physics and biology is often viewed as a sharp line, a boundary where dead matter suddenly becomes alive. But in the deep perspective of the cosmos, it is merely a gradient of complexity, a smooth transition where the laws of thermodynamics facilitate the emergence of order. The energy from the sun, filtering through the early atmosphere, struck the chemical soup of the oceans, driving reactions that combined simple molecules into more complex chains, forming amino acids, the building blocks of proteins, and nucleotides, the letters of the genes.
Tick code. These molecules were not yet alive, but they were no longer passive. They were chemical machines, driven by the flow of energy to replicate and structure themselves, exploiting the specific properties of carbon to form the intricate lattices required for biological function. Carbon, with its unique ability to form 4 stable bonds, acts as the architectural backbone of life, allowing for the creation of long, complex chains and rings that can fold into the 3-dimensional shapes necessary for enzymatic action. This element, forged in the red giant phase of dying stars and scattered by the stellar winds, found its ultimate expression in the self-replicating molecules of the early Earth, creating a direct lineage from the nuclear fusion of the past to the metabolic processes of the present. As these molecules became enclosed within lipid membranes, tiny bubbles of fat that separated the internal order from the external chaos, the first cells were born, microscopic pockets of neg entropy that maintained their structure by consuming energy from their environment. This was the moment the universe opened its eyes, not with a grand flourish, but with the microscopic twitch of a single cell, a tiny arrangement of stardust that had learned to preserve itself against the relentless pull of decay. These single-celled organisms, drifting in the currents of the primordial ocean, were the ancestors of every living thing that would ever exist, the great-grandparents of the bacteria, the plants, the dinosaurs, and eventually the human observer. The evolution of these cells required a reliable source of energy, a way to harvest the sunlight that bathed the planet, and so they developed photosynthesis, a quantum mechanical process that captures the energy of a photon and uses it to split water molecules, releasing oxygen as a waste product. This innovation, occurring some 2.5 billion years ago, triggered the Great Oxidation Event, a planetary transformation that saturated the oceans and the atmosphere with reactive oxygen, a gas that was toxic to the anaerobic life of the time, but which provided the high-energy fuel necessary for the development of complex, multicellular life. The oxygen you breathe right now, the gas that powers the metabolic fire in your mitochondria, is the legacy of these ancient microbes, a planetary inheritance that allows your brain to consume 20% of your body's energy while making up only 2% of its mass. Consider the mitochondria themselves, the tiny power plants that exist within nearly every cell of your body, generating the chemical energy
adenosine triphosphate, that drives your muscles and your thoughts. These organelles were once independent bacteria, free-living organisms that were engulfed by a larger cell in the distant past, entering into a symbiotic relationship that has endured for billions of years. They retain their own separate DNA, a circular loop of genetic code that is distinct from the DNA in the nucleus of your cells, a lingering signature of their independent origin. When you inhale, you are delivering oxygen to these ancient guests, allowing them to perform the controlled combustion of sugars that keeps you warm and alive, a biological echo of the stellar fusion that created the elements in the first place. The continuity is absolute. There is no break in the chain, no moment where the universe stopped being a physical system and started being a biological one. The iron in the hemoglobin that captures that oxygen is the same iron that stopped the heart of the star. The carbon that forms the sugar being burned is the same carbon that was dredged up from the stellar core. The water that acts as the medium for the reaction is the same water that froze on the dust grains of the solar nebula.
You are a walking museum of cosmic history, a temporary aggregation of ancient matter that has been cycling through the galaxy for 13 billion years, taking on the form of a star, a cloud, a rock, and now a person. This perspective shifts the definition of what it means to be human, moving away from the idea of an isolated entity navigating a hostile world, and toward the realization that we are a process, a localized region of high complexity within a vast interconnected system. We are not in the universe. We are the universe, a portion of the cosmos that has cooled down and organized itself sufficiently to reflect upon its own existence. The eyes with which you see the stars are built from the same elements as the stars themselves, allowing the universe to look back at its own origins, closing the loop of creation through the act of observation. As we move from the microscopic scale of the cell to the macroscopic scale of the human experience, we must recognize that this biological map is not merely a history lesson, but a guide to understanding our current state of being. The physical laws that govern the fusion of atoms and the orbit of planets are the same laws that govern the firing of neurons and the beating of the heart, creating a resonance between the macrocosm and the microcosm that has been recognized by philosophers and scientists alike. The electrical impulses that race down your nerves are driven by the movement of ions, sodium, potassium, calcium, elements that were sorted in the solar nebula and dissolved in the primordial seas, creating a battery that powers the phenomenon of consciousness. Even the solidity of your body is an illusion, a trick of the quantum forces that govern the atomic world. If we were to zoom into the atoms that make up your hand, we would find that they are almost entirely empty space, a vast void where the nucleus is a tiny speck in the center, and the electrons are distant clouds of probability orbiting far away. If the nucleus were the size of a marble sitting in the center of a football stadium, the electrons would be buzzing around the highest seats in the stands, and everything in between would be nothingness. This means that the matter that makes up your body is 99.9999999% empty space, held together not by physical contact, but by the electromagnetic fields that bridge the gaps between the particles. When you touch a surface, you are not feeling the physical collision of matter, but the repulsion of these electromagnetic fields. The electrons in your hand pushing against the electrons in the object, creating the sensation of solidity in a universe that is mostly ghost. This emptiness is not a void of nothingness, but a plenum of potential, a field of energy where particles pop in and out of existence, governed by the uncertainty principle and the strange rules of quantum mechanics. It suggests that our perception of ourselves as dense, heavy objects is merely a sensory interpretation of a much lighter, more ethereal reality, a reality where we are composed of force fields and energy patterns as much as we are composed of particles. This realization brings us to the concept of the Great Recycling, the understanding that the atoms currently residing in your body are merely on loan, borrowed from the biosphere for the duration of your life, destined to be returned to the cycle when you are done with them. The carbon atom that is currently part of a neuron in your brain may have once been part of the skin of a dinosaur, or the leaf of a prehistoric fern, or the diamond in a meteorite. It has lived 1 billion lives before it became you, and it will live 1 billion more after you are gone, moving through the soil, the air, and the water, becoming part of a tree, a bird, or perhaps another human being in a distant future. There is a profound safety in this continuity, a reassurance that while the pattern of you is temporary, the substance of you is eternal, conserved by the laws of physics that dictate that matter and energy can neither be created nor destroyed, only transformed. We are like waves on the ocean, distinct shapes that rise up from the water, travel for a time, and then crash back into the sea, losing our individual form, but remaining part of the vast, deep body of water that generated us. The wave is not separate from the ocean. It is a behavior of the ocean, just as a human being is a behavior of the universe, a temporary modulation of the cosmic field. This interconnectedness extends beyond the material recycling of atoms and into the realm of quantum entanglement, the phenomenon where particles that have interacted in the past remain linked, sharing a quantum state regardless of the distance between them. Since all matter in the universe was once compressed into a single point at the moment of the Big Bang, interacting in the searing heat of the beginning, it is theoretically possible that every particle in your body is entangled with every other particle in the cosmos, connected by invisible threads of information that span the width of the observable universe. This would imply that the separation we feel between ourselves and the stars is an illusion of scale, a failure of our senses to perceive the underlying unity of the quantum fabric. We are, in this view, not isolated observers, but integral components of a single vast organism, a cosmic web where the motion of a distant galaxy and the thought in your mind are part of the same unfolding process. The map to the stars is written in your cells because your cells are the stars, transformed by time and complexity into a vehicle for awareness. We are the mechanism by which the universe knows itself, the eyes through which it sees its own grandeur, and the mind through which it contemplates its own meaning.
As we drift further into this understanding, we begin to see the future of this biological map, the eventual fate of the matter that currently composes the Earth and its inhabitants. Just as the Sun was born from a nebula, it will eventually die, swelling into a red giant that will consume the inner planets, vaporizing the Earth and returning its atoms to the interstellar medium. This is not a tragedy, but a return, a second sowing, where the enriched material of our solar system, now containing the complex organic molecules of life, will be blown back out into the galaxy to form new clouds, new stars, and new worlds. The atoms that once formed your hands and your eyes will be part of this future nebula, floating in the void once again, waiting for the gravity of a new generation of stars to pull them together. It is possible that billions of years from now, on a planet circling a star that has not yet been born, an alien intelligence will look up at the night sky and wonder about its origins, unaware that the carbon in its body once belonged to a human being who lived on a blue planet circling a yellow sun. The cycle continues, infinite and unbroken, a great breathing of the cosmos where stars turn into life and life turns back into stars, an eternal rhythm of waking and sleeping, gathering and scattering, binding and releasing. In this vast, slow-breathing system, there is no place for fear, for there is no place where you end and the universe begins. You are safe within the walls of existence, held by the gravity that binds the galaxies, energized by the fusion that lights the suns, and constructed from the dust of the ancient forge. You are not from Earth. You are of the universe, a child of the deep time and the deep dark, finally home. To understand the biological map written within your physiology, we must first navigate back to a time before biology was possible, returning to the era known to cosmologists as the Recombination Epoch, occurring approximately
380,000 years after the initial expansion event. Before this moment, the universe was a blinding, opaque fog of superheated plasma, a chaotic soup where atomic nuclei and electrons were separated, moving with such intense thermal energy that light itself was trapped, scattering endlessly off free electrons in a state of thermodynamic equilibrium that rendered the cosmos invisible to itself. As the universe expanded, this primordial plasma began to cool, eventually dropping below 3,000 Kelvin, a critical threshold that allowed the frantic kinetic energy of the subatomic particles to slow sufficiently for protons to capture electrons, creating the first neutral atoms of hydrogen and helium. This phase transition, a sudden clearing of the cosmic fog, allowed photons to travel freely for the first time, releasing the light that we now detect as the cosmic microwave background radiation, the oldest electromagnetic signal in existence, which still permeates the room you are resting in at this very moment. Following this release of light, the universe entered an era known as the Cosmic Dark Ages, a period lasting hundreds of millions of years where no stars existed to illuminate the void, and the cosmos was filled almost entirely with neutral hydrogen gas, drifting in the silent, expanding dark. It is here, in this profound silence and simplicity, that the first stroke of your biological portrait was painted, for the hydrogen that dominates the composition of the universe during this epoch is identical to the hydrogen that currently resides within the water molecules of your cells. When you drink a glass of water, you are ingesting atoms that were forged in the aftermath of the Big Bang, protons that have existed for 13.8 billion years, drifting through the vacuum, cycling through stars, and eventually finding their way into the hydrosphere of Earth.
The hydrogen atom is the simplest of all chemical structures, consisting of a single proton and a single electron. Yet it is the primary canvas upon which the complexity of life is drawn, comprising nearly 2/3 of the atoms in the human body. Consider the stability of this element. The proton at the heart of a hydrogen atom is estimated to have a half-life far longer than the current age of the universe, meaning that the foundational bricks of your physical form are, for all practical purposes, eternal.
During the cosmic dark ages, this hydrogen was not yet part of any structure, but was distributed in vast, diffuse clouds that stretched across millions of light years, creating a structureless monotony that defies human comprehension. However, this uniformity was not perfect. Quantum fluctuations from the earliest moments of the universe had left microscopic irregularities in the density of the gas, creating regions where the hydrogen was slightly more concentrated than the surrounding vacuum. These overdensities, though minute, acted as gravitational seeds, exerting a faint but persistent pull on the surrounding gas, initiating a process of accumulation that would span eons. Gravity, the weakest of the four fundamental forces, requires immense timescales to sculpt structure from gas. But in the absolute stillness of the early universe, it had no competition. Slowly, inexorably, the hydrogen atoms began to fall toward these centers of density, their individual motions bending toward the collective mass, creating currents of gas that flowed through the dark like invisible rivers. As the gas converged, the clouds became more massive, increasing their gravitational influence and drawing in material from even greater distances, a self-reinforcing cycle known as gravitational instability. The physics governing this collapse are dictated by the Jeans instability criteria, which describes the balance between the internal gas pressure pushing outward and the
gravitational force pulling inward. For millions of years, the gas pressure was sufficient to resist the collapse, keeping the clouds diffuse and cool. But as the mass of the accumulating hydrogen crossed a critical threshold, gravity finally overcame the thermal resistance. The cloud began to fragment and collapse in on itself, the atoms crowding closer together, their potential energy converting into kinetic energy and then into heat. Deep within these collapsing clouds, the temperature began to rise, climbing from the near absolute zero of deep space to hundreds, then thousands, then millions of degrees. This was not a violent explosion, but a slow, crushing embrace, a heating generated by the friction of atoms being forced into a space too small to contain them. This compression continued until the core of the cloud reached a temperature of approximately 10 million Kelvin, a thermal environment so extreme that the electrons were stripped from their protons once again, recreating the plasma state of the early universe within a localized sphere. At these energies, the protons, which normally repel each other due to their positive electric charge, were moving with such velocity that they could overcome the Coulomb barrier, the electrostatic force field that protects the nucleus. When two protons collide at these speeds, they confuse, merging to form a heavier nucleus and releasing a tiny burst of energy in the process, a phenomenon known as nuclear fusion. This moment, the ignition of the first nuclear fire, marked the end of the cosmic dark ages and the birth of the first generation of stars, known to astronomers as population 3 stars. These primordial stars were unlike the sun that warms our planet today. They were composed almost entirely of hydrogen and helium, lacking the heavy elements that make up rocky planets and biological organisms.
Because they lacked these cooling elements, they had to be massive to initiate fusion, often growing to hundreds of times the mass of our sun,
burning with a ferocious, ultraviolet intensity that illuminated the surrounding gas and began to re-ionize the universe. Yet, despite their power, these first stars were sterile. They contained no carbon, no oxygen, no iron, and therefore they could not possess planets, nor could they harbor life. They were simply engines of conversion, vast fusion reactors designed by the laws of physics to transmute the simple hydrogen of the Big Bang into the heavier, more complex elements required for biology. The light from these stars, traveling through the expanding fabric of space, carried the first photons generated by fusion, signaling that the universe had begun the long process of nucleosynthesis. Inside the cores of these giants, the proton-proton chain reaction was efficiently converting hydrogen into helium, releasing energy in the form of gamma rays that slowly worked their way to the surface. This process, the fusion of hydrogen into helium, is the primary source of energy for the majority of stars in the universe, including our own sun, and it represents the first step in the chemical ladder that leads to human consciousness. The helium ash that accumulated in the cores of these population 3 stars was not merely waste. It was the raw material for the next phase of cosmic evolution, a substance waiting for the temperature to rise further. As the hydrogen fuel in the core was exhausted, the outward pressure of radiation ceased, and gravity, always waiting, resumed its crushing grip on the star. The core contracted, the temperature spiked, and the star began to burn helium, fusing it into heavier elements. But even this was not enough to create the full periodic table required for a human being. It is essential to recognize that the universe did not begin with the capacity for life. It had to build that capacity, atom by atom, through the life cycles of these massive, short-lived stars. The hydrogen that forms the water in your body is a survivor of this era, a witness to the first light, while the other elements in your tissues were yet to be born, waiting in the potentiality of nuclear physics. The sheer scale of this preparatory phase is difficult to internalize. For hundreds of millions of years, the universe was simply a machine for processing hydrogen, a vast, silent factory operating without observers. The gravitational collapse of these gas clouds, the ignition of the first stars, and the subsequent synthesis of helium were all necessary precursors, a laying of the foundation for the chemical complexity that would eventually emerge. We often view the emptiness of space as a void, but it is more accurately described as a reservoir, a storage medium for the primordial hydrogen that has not yet been processed into stars. Between the galaxies, filaments of this gas still stretch across the cosmos, the cosmic web that connects all massive structures, a remnant of the initial distribution of matter. Your connection to this era is direct and physical. The proton in the hydrogen atom of your DNA is indistinguishable from a proton in the core of a population 3 star, or a proton drifting in the intergalactic medium. In the context of quantum mechanics, particles of the same type are identical. They do not have individual identities or histories that distinguish them from one another, meaning that the hydrogen in you is effectively the same hydrogen that filled the universe during the Dark Ages. This element, the simplest in existence, acts as the carrier of mass, the fuel of stars, and the bond that holds your molecular structure together.
It is the bridge between the high-energy physics of the early universe and the delicate biochemistry of a living cell. A substance that can endure the heart of a star and the interior of a neuron with equal stability.
As we descend further into the history of matter, we must transition from the simple canvas of hydrogen to the complex pigments of life, a transition that requires us to look deep into the dying moments of these first stars. The universe, having established the light, now needed to invent the chemistry of solids, a task that required temperatures and pressures far exceeding the ignition point of hydrogen. The creation of the heavier elements, the carbon that forms the backbone of your organic molecules, the nitrogen in your amino acids, and the oxygen that drives your metabolism, required a different kind of furnace. These elements are not primordial. They did not exist in the initial fireball of the creation event, nor could they be formed in the stable, long-burning phase of a main sequence star. To understand where the substance of your body originated, we must examine the specific nuclear reactions that occur when a star exhausts its primary fuel and begins to consume its own hash.
Imperfectity. This reaction is the bottleneck of life. Without it, the universe would remain a sterile expanse of hydrogen and helium, devoid of the complex chains and rings that carbon chemistry allows. Every atom of carbon in your body, from the strands of your DNA to the glucose powering your brain, was forged in this rare three-way collision deep within the crushing interior of a dying star. Once the carbon is formed, it acts as a catalyst and a seed for further reactions, capturing additional helium nuclei to form oxygen, the element that you are breathing in and out as you listen to this. The star, now possessing a core of carbon and oxygen, becomes a layered structure, resembling a cosmic onion, with shells of different fusion reactions occurring at different depths. In the outermost shell, hydrogen still fuses into helium. Below that, helium fuses into carbon. And in the deep, dense center, carbon and oxygen are subjected to pressures that force them to fuse into even heavier elements, like neon, magnesium, and silicon. This stratification of the stellar core is a manufacturing process of immense precision, separating the elements by weight and binding energy, preparing them for their eventual release. The star is no longer just a source of light. It has become a womb for matter, a high-pressure vessel where the raw materials of future planets are being synthesized. However, this process of fusion cannot continue indefinitely. It is limited by the laws of thermodynamics and the binding energy of the atomic nucleus. As the star fuses ever heavier elements, it extracts less and less energy from each reaction, eventually reaching a point where the fusion process consumes energy rather than releasing it. This limit is found at the element iron, specifically the isotope iron-56, which possesses one of the most tightly bound nuclei in physics, making it the ash of the stellar furnace, the point where the fire goes out.
When the core of a massive star is converted into iron, the outward pressure that supports the star against gravity vanishes in an instant, triggering a catastrophic collapse that occurs in a fraction of a second. This collapse is the prelude to the supernova, the explosive event that will scatter these newly forged elements across the galaxy, seeding the interstellar clouds with the dust of life. But before we witness that explosion, we must linger on the quiet, millions of years long accumulation that precedes it, the slow breathing of the galaxy as it gathers the gas required to build a star. Consider the patience of this system. The gas that formed our sun and subsequently the Earth and your body drifted for billions of years before gravity finally pulled it together. It was enriched by the deaths of thousands of previous stars, each contributing a dusting of heavy elements to the mix, a cosmic heritage that is recorded in the isotopic ratios of the rocks beneath your feet. The water you drink, the air you breathe, and the ground you walk on are all recycled materials, composed of atoms that have been part of countless other systems before they became part of you. In the context of the cosmic guide, we see that you are not a static object, but a temporary pattern in a continuous flow of matter, a standing wave in the river of space-time. This perspective shifts the definition of self from a biological organism to a geological and cosmological process, blurring the lines between the living and the non-living. The iron in your blood is not just similar to the iron in a meteorite, it is the same iron, forged in the same type of stellar crucible, governed by the same quantum rules. The distinction between you and the universe is merely a linguistic convention, a useful shorthand for navigating the macroscopic world, but it dissolves when viewed through the lens of nuclear physics.
At the atomic level, there are no boundaries, only fields of probability and interactions of energy, a seamless fabric that extends from the center of your consciousness to the edge of the observable universe. As we drift through the narrative of the hydrogen atom, we can visualize the immense clouds of the Orion Nebula, a stellar nursery where new stars are being born today, repeating the process that created our solar system 4.5 billion years ago. These clouds are illuminated by the ultraviolet radiation of massive young stars, causing the hydrogen gas to glow with a deep red hue, a visual signature of the electron transitions occurring within the atoms. This red glow, known as H-alpha emission, is the color of creation, the visible evidence that the universe is still active, still forging new systems from the primordial reserves. When you look at an image of a nebula, you are seeing the raw material of future worlds, the unformed potential of biology waiting for gravity to do its work. The timescale of this process is soothing in its magnitude. The collapse of a gas cloud into a protostar takes hundreds of thousands of years, a slow-motion descent that is imperceptible to the human eye. It is a gentle gathering, a soft accumulation of mass that occurs in the quiet dark, far removed from the frantic pace of biological life. In this slow time, there is no urgency, no deadline, only the inevitable interaction of mass and gravity playing out according to the deterministic laws of physics. The universe is in no rush to create, it has ample time, and the result of this patience is the stability of the stars that light our night sky. The stability of a star like our Sun is maintained by a delicate balance known as hydrostatic equilibrium, where the inward pull of gravity is perfectly matched by the outward pressure of the hot gas. This balance can be maintained for 10 billion years, providing a steady, unchanging source of energy that is essential for the evolution of life. If the sun were to fluctuate significantly in brightness, or if its lifespan were measured in millions rather than billions of years, the slow process of biological evolution would never have had the time to unfold. The reliability of the proton-proton chain reaction, the consistent output of energy from the solar core, is the metronome of life, the steady rhythm that allows the complex chemistry of DNA to replicate and diversify. We must also consider the role of the magnetic fields that thread through these gas clouds, invisible lines of force that guide the motion of the charged particles. In the early stages of star formation, these magnetic fields can act as a brake, slowing the rotation of the collapsing cloud and allowing the material to fall inward rather than spinning apart. This interaction between gravity, turbulence, and magnetism is a complex dance of fluid dynamics, a magneto-hydrodynamic struggle that determines the final mass and rotation of the newborn star. It is a chaotic process, yet it produces a highly ordered result, a spherical star surrounded by a flattened disk of gas and dust, the protoplanetary disk. It is within this disk that the story of the planets begins, where the dust grains, composed of silicon, iron, and carbon soot, begin to collide and stick together. These microscopic collisions are the first steps in the construction of a world, the accretion of solid matter from the diffuse cloud. But before the planets can form, the star must clear the area, blowing away the remaining volatile gases with its powerful stellar wind. This T Tauri phase of the young star is a period of intense activity, where the star asserts its dominance over the surrounding space, carving out a cavity in the nebula.
The material that remains, the rocky debris and the icy comets, is the residue of star formation, the leftovers that will eventually coalesce into a planetary system. The Earth, in this view, is a survivor, a collection of heavy elements that manage to avoid falling into the sun or being ejected into interstellar space. The specific mixture of elements on Earth, the abundance of oxygen, silicon, aluminum, and iron, is a direct reflection of the specific history of the supernova explosions that enriched our local region of the galaxy. If the mix had been slightly different, the chemistry of our planet, and therefore the biology of our bodies, would be radically different. We are, in a very literal sense, the local flavor of the galaxy, a sample of the cosmic soup taken from this particular spiral arm at this particular moment in time. The calcium in your bones, which gives you the strength to stand against gravity, is a metal that is typically produced in the explosion of white dwarf stars, a specific type of supernova known as type AA. These explosions are the universe's primary source of calcium, scattering it across the cosmos to eventually find its way into the limestone of the Earth and the skeleton of a vertebrate. Without these violent events, life would be soft, unable to build the rigid structures required for movement and protection. So, when we speak of the canvas of hydrogen, we are speaking of the beginning, the blank page upon which the violent and beautiful history of nucleosynthesis has been written. The hydrogen is the background, the medium that carries the heavier, rarer elements that make up the complexity of existence. It is a medium that is both ancient and active, forming the bridge between the Big Bang and the present moment. As you rest, the hydrogen in your body continues to vibrate, its electrons jumping between energy levels, absorbing and emitting photons in a quantum dance that has not ceased since the era of recombination. This is the continuity of matter, the unbroken line that connects you to the source of all things. You are not separate from this history. You are the current iteration of it, the leading edge of a wave that began 13.8 billion years ago. The complexity of your biology is built upon the simplicity of this physics, a towering structure of emergent properties that rests on a foundation of protons and electrons. And as we continue to explore this map, we will see how these simple atoms, forged in the dark and cooked in the stars, came to arrange themselves into the molecules of life, creating a vehicle capable of wondering about its own origin. The journey from hydrogen to human is a path of increasing order, a local reversal of entropy driven by the flow of stellar energy. It is a path that we will trace in detail, following the atoms as they move from the fusion core to the supernova shockwave, from the interstellar cloud to the planetary surface, and finally into the intricate lattice of the living cell. But for now, let us rest in the simplicity of the beginning, in the quiet, cooling dark of the early universe, where the only sound was the hum of the baryon acoustic oscillations, ripples in the density of the primordial gas. These sound waves, traveling through the plasma of the young cosmos, determined the large-scale distribution of galaxies, creating the template for the structure of the universe we see today. The scale of these waves is immense, with wavelengths measuring hundreds of thousands of light-years, yet they are physically related to the sound waves that carry a human voice. It is a resonance that spans the scales, a harmonic connection between the largest structures in the universe and the smallest vibrations of the air. In this vast, resonant quiet, the hydrogen waits, it gathers, it cools, and slowly, inevitably, it prepares to light the first fires, ending the dark ages and inaugurating the era of stars. This is the canvas.
This is the beginning of the map, and you are there, present in the potential of the atoms, waiting to be born. From this silent, dark accumulation of primordial gas, we witness the emergence of the universe's primary engine, a mechanism defined not by the chaotic explosion of a bomb, but by the precise, enduring crushing of matter into a new state of existence. As gravity continues its inexorable work, drawing the vast clouds of hydrogen inward, the potential energy of the gas is converted into kinetic heat, raising the temperature of the core from the frigid, near absolute zero of the void to thousands and then millions of degrees. This is not a sudden event, but a gradual, agonizing contraction, a gravitational tightening that squeezes the atoms closer together until they are stripped of their electron shells, creating a state of matter known as plasma, where nuclei float freely in a sea of electric charge. It is here, in the deep, crushing dark of the protostar's core, that the universe encounters a fundamental barrier, a resistance known as the Coulomb repulsion, which dictates that positively charged protons must repel one another with significant force. For a star to ignite, for the lights of the galaxy to turn on, gravity must overcome this electromagnetic shield, forcing the protons so close together that they cross a threshold governed not by classical mechanics, but by the probabilistic laws of quantum physics. We call this phenomenon quantum tunneling, a reality where a particle does not surmount a barrier by energy alone, but rather borrows energy from the vacuum to appear on the other side. A statistical impossibility in the macroscopic world that becomes a necessity in the subatomic realm. When the core temperature reaches approximately 15 million Kelvin, the thermal velocity of the protons becomes sufficient to allow this tunneling to occur, initiating the proton-proton chain reaction, the fundamental metabolic process of the main sequence star.
It is a sequence of events that is both incredibly violent and paradoxically stable. A continuous thermonuclear detonation that is contained by the crushing weight of the star's own outer layers. In the first step of this stellar alchemy, two protons, which have existed as distinct entities since the first moments of the Big Bang, are forced into a union that transforms one of them into a neutron, releasing a positron and a neutrino in the process. This transformation creates a nucleus of deuterium, a heavy isotope of hydrogen, and it is the rate-limiting step of the entire reaction, occurring so rarely for any individual proton that the average hydrogen atom can wander through the core of a star for billions of years before it successfully fuses. This inherent slowness is a mercy, a cosmic governor that prevents the star from consuming its fuel in a single catastrophic flash, ensuring instead that it burns with a steady, warming glow for eons. The positron produced in this merger almost immediately encounters an electron, its antimatter counterpart, and the two annihilate one another, converting their entire mass into pure energy in the form of gamma rays, the most potent form of light in the universe. Simultaneously, the neutrino, a ghost-like particle with almost no mass and no electric charge, escapes the core instantly, passing through the dense layers of the star and out into the cosmos without interacting with a single atom, carrying away a small fraction of the energy as a silent herald of the fusion occurring deep within. Meanwhile, the newly formed deuterium nucleus is quickly struck by another proton, fusing to form helium-3 and releasing yet another gamma ray, adding to the growing reservoir of photon energy trapped within the core. Finally, in the culmination of this chain, two helium-3 nuclei collide, merging to form a stable helium-4 nucleus and ejecting two protons back into the plasma to begin the cycle anew, a perfect circle of consumption and
creation that results in a net loss of mass. This missing mass, the difference between the weight of the ingredients and the weight of the final product, is converted directly into energy according to Einstein's equivalency principle, creating the outward pressure that holds the star up against the crushing dark. This state of balance is known as hydrostatic equilibrium, a dynamic tension where the inward pull of gravity is perfectly counteracted by the outward push of thermal expansion, creating a stable sphere of plasma that can endure for 10 billion years. It is a stillness born of opposing violences, a celestial standoff that allows the star to maintain a constant size and temperature, providing the long-term stability required for the evolution of complex chemistry on any orbiting worlds. The star is not merely burning, it is regulating itself, adjusting its rate of fusion to match the weight of its layers, breathing in a rhythm so slow that it appears motionless to the human eye. However, The light generated by this fusion does not immediately escape to bathe the solar system in warmth. Rather, it begins a torturous, chaotic journey from the core to the surface, a pilgrimage that spans thousands of years. The core of the star is so dense, comparable to compressing the mass of an aircraft carrier into the volume of a grain of sand, that the gamma-ray photons produced by fusion can travel only a fraction of a millimeter before colliding with a charged particle, being absorbed and re-emitted in a random direction. This process, known as the random walk or radiative diffusion, means that a photon may bounce trillions of times within the radiative zone, slowly losing energy and shifting its wavelength from the deadly gamma spectrum down to X-rays, then ultraviolet, and finally into the visible spectrum. The light that strikes your retina today, the warmth you feel on your skin, began its journey in the core of the sun during the last ice age.
The stellar interior, while humanity was still painting in caves, only to emerge from the photosphere 8 minutes ago. This delay creates a profound disconnection between the cause and the effect, a temporal lag that means the sun we see is a ghost of its own history, broadcasting the energy of a fusion event that occurred in a prehistoric era. As the energy moves outward, it passes from the radiative zone into the convective zone, where the plasma becomes opaque and begins to boil like a pot of thick soup, carrying the heat to the surface in massive rolling columns of gas that are larger than the Earth itself. These convective cells rise, release their heat into the vacuum of space, and then cool and sink back down to pick up more energy, creating a granular texture on the surface of the star that churns with the slow, rhythmic motion of a lava lamp. When the photon finally breaks free from the solar surface, it enters the vacuum of space, traveling at the absolute speed limit of the universe, crossing the 150 million kilometers to Earth in a straight, uninterrupted line. Upon arrival, this packet of stellar energy drives the entire biosphere, powering the winds, the currents of the ocean, and the biological machinery of every living thing. It is here that we find the biological bridge, the direct link between the nuclear physics of the core and the biochemistry of the cell. Consider the plant leaf, a biological solar panel that has evolved to capture this specific frequency of light, utilizing the energy to split water molecules and forge bonds between carbon atoms. The process of photosynthesis is, in essence, a reversal of the fusion process. Where the star fuses atoms to release energy, the plant uses that energy to bond atoms, storing the sunlight in the chemical bonds of glucose. When you consume food, whether it is a plant or an animal that ate a plant, you are breaking those bonds, releasing the stored solar energy to power the movement
of your muscles and the firing of your neurons. The heat that keeps your body warm is the liberated heat of the sun, delayed by a journey of 1 million years through the radiative zone and a few months through the food web. But it is the same energy, conserved and transferred across the void. You are, in a very literal thermodynamic sense, a metabolic engine running on the exhaust of a star, processing the photons that were forged in the proton-proton chain to maintain the order of your own biology against the chaotic pull of entropy. The ATP molecules that shuttle energy within your cells are the batteries that hold this captured starlight, releasing it in microbursts to fuel the replication of DNA, the synthesis of proteins, and the beating of your heart. Without the specific tuning of the sun's fusion rate, Without the precise balance of the weak nuclear force that governs the conversion of protons to neutrons, the sun would either burn out too quickly for life to evolve, or burn so dimly that the Earth would remain a frozen rock. The stability of the proton-proton chain is the metronome of biological time, a constant, unwavering beat that has allowed the slow, meandering process of evolution to unfold over 4 billion years without interruption. If the sun were a variable star, prone to wild fluctuations in output, the delicate chains of amino acids that formed in the primordial oceans would have been denatured by heat or frozen by cold before they could assemble into the first cells. It is the patience of the star, its ability to maintain hydrostatic equilibrium for geologic eons, that provides the safe harbor necessary for the universe to organize itself into complex, thinking matter. But the sun does more than simply provide energy. It acts as a transmuter of elements, a cosmic kiln that is slowly changing the composition of the universe, atom by atom, fusing the primordial hydrogen into helium, and altering the metallicity of the galaxy.
In the core, the ash of this fusion fire, the helium-4 nuclei, accumulates, sinking to the center and slowly increasing the density and temperature of the star, a process that will eventually force the sun to evolve away from the main sequence. This accumulation is a record of time, a chemical clock that ticks forward with every fusion event, marking the age of the star and the depletion of its primary fuel source. For the human body, however, the sun's current phase is the only one that matters, a Goldilocks era of stellar luminosity that permits liquid water to exist on the surface of our planet, a condition that is rare and precious in the vast, hostile dryness of the cosmos. The water in your cells, the medium in which all your biochemistry occurs, is kept in its liquid state solely by the thermal bath provided by the sun, a continuous infusion of kinetic energy that prevents the molecules from locking into the rigid crystal lattice of ice. This relationship between the fusion core and the living cell is one of absolute dependency, a tether of light that connects the subatomic interactions of the solar interior to the macroscopic experience of being alive. We must also consider the magnetic nature of this stellar womb, for the sun is not merely a ball of gas, but a dynamo of twisting magnetic field lines, generated by the differential rotation of its plasma layers. Because the sun is fluid, its equator rotates faster than its poles, dragging the magnetic fields through the plasma, winding them up like rubber bands until they snap, releasing bursts of high-energy particles known as solar flares. These ejections of plasma travel through the solar system, washing over the planets and interacting with their magnetospheres, creating the auroras that dance in the polar skies of Earth. These geomagnetic storms are the breath of the star, a reminder that our parent star is an active, dynamic body, capable of influencing the environment of Earth in ways that go beyond simple illumination. Yet even in this activity, there is a protective aspect. The sun's magnetic field, the heliosphere, extends far beyond the orbit of Pluto, creating a bubble that shields the entire solar system from the high-energy cosmic rays of the interstellar medium. We live inside the atmosphere of the sun, protected by its magnetic influence, drifting within the protective wake of its passage through the galaxy. The fusion process itself relies on the fundamental constants of the universe being tuned to a razor's edge. If the strong nuclear force were just a few percent stronger, the diproton, two protons stuck together, would be stable,
and all the hydrogen in the universe would have fused into helium in the first few minutes of the Big Bang. In such a universe, there would be no water, no long-lived stars, and no hydrogen fuel to power the slow burn required for life. The cosmos would be a helium-filled wasteland, devoid of the chemical complexity we observe. Conversely, if the strong force were slightly weaker, deuterium would not hold together, and the proton-proton chain would be impossible, leaving the universe dark and cold, filled with sterile hydrogen clouds that never ignite. We exist in the narrow window of probability where fusion is possible but difficult, a bottleneck in physics that allows stars to function as long-term storage batteries for the universe's energy. This difficulty is what grants us time. It is the inefficiency of the proton-proton chain that buys the billions of years required for a single cell to evolve into a civilization. The light that illuminates your room, the glow of the screen, the energy that allows your brain to process these words, all of it is the result of protons struggling to overcome their mutual repulsion, a struggle that has been playing out in the dark heart of the star for 4.5 billion years.
As we visualize this process, we can imagine the core not as a place of chaos, but as a vast, vibrating lattice of collisions, a dense fog of particles moving at lightning speeds, yet governed by strict statistical laws that ensure the stability of the whole. It is a machine of exquisite precision, self-correcting and self-sustaining, converting the raw stuff of the Big Bang into the usable currency of light. And as this light travels outward, it carries with it the information of its origin, the spectral fingerprint of the hydrogen and helium that birthed it, a message that we have learned to decode with our telescopes and spectroscopes. But the story of nucleosynthesis does not end with helium. The proton-proton chain is merely the first gear of the stellar engine, the preliminary stage of a process that will eventually yield the structural elements of the cosmos. While the Sun is content to fuse hydrogen for its entire main sequence life, there are other stars, more massive and shorter-lived, that possess the gravitational pressure to push beyond this initial barrier. In these giants, the crushing weight of the outer layers forces the core to contract further, raising the temperature to 100 million Kelvin, a threshold where the ash of the hydrogen fire, the helium, can itself become the fuel. This is the transition from the simple to the complex, the moment where the universe begins to forge the backbone of biology, creating the heavy, versatile atoms that will one day form the chains of DNA. The patience of the hydrogen burning phase sets the stage, preparing the stellar crucible for the next act of creation, where the triple alpha process will defy the odds to weave 3 helium nuclei into a single atom of carbon. But before we descend into that deeper, hotter fire, we must acknowledge the profound stillness of the current era, the long, stable summer of the universe, where stars like our Sun provide the consistent, gentle energy required for water to remain
in liquid and for carbon to organize. The hydrogen atom, the simplest of all structures, consisting of a single proton and a single electron, is the hero of this epoch, the fuel that drives the galaxy and the blanket that keeps the night at bay. It is the most abundant element in your body, present in every molecule of water, every protein, every strand of fat, a direct material connection to the primordial cloud and the stellar core. When you drink a glass of water, you are consuming the ashes of the Big Bang, combined with the oxygen forged in a dying star, energized by the light of the current sun, a cocktail of cosmic history that sustains your existence from moment to moment. The stability of this system allows us to sleep,
to plan for tomorrow, to trust that the sun will rise and the physics of the universe will remain constant. The hydrostatic equilibrium of the sun is mirrored by the homeostasis of your own body, a biological equilibrium that maintains your temperature, your pH, and your energy levels within a narrow, safe range. Just as the star balances gravity and fusion, your body balances consumption and expenditure, a fractal echo of the cosmic process occurring on a microscopic scale. In the quiet drift of the cosmos, the fusion continues, silent to our ears, but deafening in its energy release, a roar of light that permeates the solar system. The neutrinos stream through your body at a rate of trillions per second, passing through the Earth as if it were made of mist, a ghostly reminder of the reaction occurring 93 million miles away. We are transparent to the core of the star, yet dependent on its surface, living in the Goldilocks zone of interaction, where the energy is neither too intense to destroy us, nor too weak to sustain us. This is the stellar womb, the warm, illuminated cavity in the cold universe, where matter is allowed to wake up.
It is a temporary shelter, built by gravity and powered by the strong nuclear force. A bubble of order in a universe that tends toward disorder. And within this bubble, the hydrogen waits, the helium accumulates, and the clock ticks slowly toward the moment when the fuel will run low, and the star will be forced to change, to evolve, and to begin the next phase of the great recycling. But for now, the balance holds. The protons merge. The gamma rays begin their long climb, and the light flows outward in a steady, unbroken stream, carrying the promise of warmth to the blue planet circling in the distance. The machinery of the heavens is functioning within tolerance, operating with the smooth, silent efficiency of a system that has been refined over 13 billion years. There is no urgency here, only the deep, rhythmic pulse of the fusion cycle, a heartbeat that spans eons, creating the conditions for the miracle of chemistry to take hold. As we prepare to look deeper into the furnace, to witness the forging of the elements that give us form and structure, we rest in the knowledge of this stability. We acknowledge the hydrogen that burns to keep us warm, the gravity that holds the reactor together, and the vast, empty distances that the light must cross to reach us. It is a system of immense power, yet it is gentle enough to tickle the retina of an eye, to warm the surface of a leaf, to lift the vapor from the ocean. The violence of the core is sequestered, hidden behind 1,000,000 miles of plasma, filtered and softened until it becomes the gentle daylight that wakes the world. This is the gift of the main sequence, the long pause in the collapse that allows for the existence of the observer. And in this pause, we find our place, suspended between the fire and the void, held by the gravity of a star that is slowly, patiently, turning itself into light.
To understand the origin of the biology that currently sustains your consciousness, we must look backward, past the stability of our current sun, past the formation of the Earth,
and into the deep, resonant silence of the primordial epoch, before there were planets to host life, or carbon to build chains of DNA, or even the heavy elements required to form a rocky surface. There was only the canvas of the void, a vast and expanding theater filled with the simplest, most elegant form of matter. This was the era of the cosmic dark ages, a period of time stretching for hundreds of millions of years, where the universe was devoid of starlight, existing as a cooling sea of neutral gas that permeated every corner of existence with a uniform, suffocating fog. It is difficult for the human mind, accustomed to the contrast of bright stars against a black sky, to visualize a universe without point sources of light. But this was the state of reality for an expanse of time that dwarfs the history of the human species. In this early universe, following the initial rapid expansion and the subsequent cooling that allowed energy to condense into matter, the cosmos was dominated by a single overwhelming presence: hydrogen. This is the element of beginnings, the fundamental building block from which all complexity is eventually derived, consisting of a single proton holding a single electron in a delicate electromagnetic embrace. It is the simplest possible atom, a structure of such elemental purity that it accounts for the vast majority of baryonic matter in the universe, and it is the primary inheritance that your body has received from the Big Bang itself. When you drink a glass of water or feel the blood pumping through your veins, you are interacting with hydrogen atoms that were forged in the first 3 minutes of time, artifacts of creation that have remained unchanged for 13.8 billion years.
These hydrogen atoms are the elders of your biological system, far older than the carbon in your muscles or the calcium in your bones. Ancient travelers that have witnessed the entire history of the cosmos before finding a temporary residence within your cells. They are the silent witnesses to the evolution of the galaxy, having drifted through the intergalactic medium for eons, participating in the formation of nebulae, the birth of stars, and the condensation of planetary oceans, yet remaining fundamentally unaltered in their nuclear structure. This continuity connects you directly to the moment of recombination, the era when the universe cooled sufficiently for protons to capture electrons, turning the opaque plasma of the early cosmos into a transparent gas, allowing light to travel freely for the first time. The universe at this stage was a place of profound stillness, a near-perfect vacuum filled with this hydrogen fog and a smaller component of helium, drifting in the dark, governed only by the expansion of space and the subtle, whispering influence of gravity. There was no chemistry as we understand it, no complex molecular interactions, only the simple thermodynamic movements of gas atoms colliding in the void, transferring kinetic energy in a ceaseless, invisible dance. But the universe is not static, and even in this uniformity there were imperfections, tiny fluctuations in density that had been imprinted on the fabric of spacetime during the earliest moments of inflation. These overdensities, regions where the gas was slightly more concentrated than the surrounding average, became the seeds of structure, the gravitational anchors that would eventually give rise to the galaxies. Gravity, in this context, acts not as a violent crusher, but as a patient gatherer, a force of accumulation that works over timescales that are almost geological in their slowness.
In these slightly denser regions, the gravitational pull was marginally stronger than the expansion of the universe, creating a delicate imbalance that caused the hydrogen gas to slow its outward drift and begin to fall inward. This was not a rapid collapse, but a gentle coalescing, a slow-motion sedimentation of gas falling into the potential wells created by dark matter halos, gathering the diffuse mist of the universe into distinct, massive clouds. As the gas fell, it carried with it the potential for everything that would come later, holding the raw material for every star, every planet, and every living organism that would ever exist, suspended in a state of cold, dark potentiality. This process, known as the gene's instability, dictates that a cloud of gas will collapse when its internal pressure, generated by the thermal motion of its atoms, is no longer sufficient to counteract the inward pull of its own gravity, a tipping point that transforms a stable nebula into a star-forming region. In the early universe, because the gas was warmer and the clouds were composed only of hydrogen and helium without heavier elements to help radiate away heat, these collapsing clouds had to be immense, containing mass equivalent to hundreds or thousands of suns. The collapse continued for millions of years, the gas becoming denser and hotter as it fell toward the center, converting gravitational potential energy into thermal energy, slowly raising the temperature of the core from the near absolute zero of deep space to the millions of degrees required for ignition. It is a paradox of astrophysics that the coldness of space is the necessary precursor to the heat of the stars, for it is only in the cold, dense molecular clouds that gravity can overcome the thermal pressure of the gas, allowing the collapse to proceed. As the cloud contracts, it begins to spin, conserving angular momentum, flattening into a disk that rotates around the growing protostar at the center, a dark,
turbulent womb where the density climbs higher with each passing millennium. Deep inside this collapsing structure, the hydrogen atoms are pressed closer and closer together, their electron shells overlapping, the pressure mounting until the atoms are stripped of their electrons, returning to the state of plasma that existed at the beginning of time. The core of the protostar becomes a chaotic, high-energy environment where protons hurtle toward one another at significant fractions of the speed of light, repelled by their positive electric charges, but pushed together by the crushing weight of the unimaginable mass above them. This is the Coulomb barrier, the electrostatic wall that prevents atomic nuclei from touching, a barrier that requires extreme temperatures to overcome. For eons, the cloud merely glows with the heat of compression, a dark red ember in the infrared spectrum, invisible to the naked eye, slowly gathering its strength, waiting for the moment when the temperature crosses the critical threshold of 10 million Kelvin. And then, in the deep, isolated dark of the early universe, the threshold is crossed. A proton, moving with sufficient thermal velocity, tunnels through the electrostatic barrier of another proton, driven by the probabilistic nature of quantum mechanics, and the two fuse together. This event, the proton-proton chain reaction, releases a tiny flash of energy, a gamma ray, that is born in the crushing dark of the core. It is followed by another and another, the reaction rate climbing exponentially as the heat generated by the fusion stimulates further fusion, creating a runaway effect that ignites the entire core. The star takes its first breath. The outward pressure of the fusion energy strikes the infalling gas, halting the collapse, establishing a new equilibrium, a hydrostatic balance where the force of gravity trying to crush the star is perfectly countered by the force of the nuclear fire pushing outward. The Dark Ages end, not with a whimper, but with the sudden, brilliant ignition of the first generation of stars, known to astronomers as Population 3 stars.
These were not like the sun that warms your face today. They were titans, monsters of pure hydrogen and helium, burning with a blue-white intensity that radiated across the ultraviolet spectrum, illuminating the surrounding gas and reionizing the universe. These stars were the first engines of creation, the first distinct objects to separate themselves from the background fog, colossal spheres of plasma that lived fast and burned with a ferocity that depleted their fuel in a fraction of the time of a modern star. Because they lacked the heavy elements that act as coolants in modern star formation, they were inefficient at radiating heat, which meant they had to be massive to form, often hundreds of times the mass of the sun. Their light was harsh and energetic, carving out bubbles of transparency in the surrounding neutral gas, ending the cosmic dark ages and ushering in the era of stellar synthesis. But for all their grandeur, these first stars were composed of only the simplest materials, hydrogen and helium, which meant they lacked the chemical complexity to form planets for life. A solar system formed around a population 3 star would have been a barren, gaseous place, devoid of rock, metal, water, or organic molecules. There could be no Earth, no biology, no consciousness to observe the brilliance of the blue giants, because the universe had not yet invented the carbon required for chemistry or the oxygen required for water. The cosmos was bright, but it was sterile, a gallery of magnificent lights shining on nothing but drifting gas. However, the purpose of these stars was not to nurture life, but to act as the forges that would create the possibility of life. Deep within their cores, the alchemy of the universe had begun.
The hydrogen that had existed since the Big Bang was being crushed into helium, releasing the energy that powered the star. But as the hydrogen supply in the core began to dwindle, the star was forced to contract further, raising the temperature even higher. This contraction is the mechanism of evolution for a star, a desperate attempt to maintain equilibrium that inadvertently unlocks new pathways of nucleosynthesis. As the core temperature rises to 100 million Kelvin, the helium ash left over from the hydrogen burning becomes the fuel for a new reaction. 3 helium nuclei colliding in a nearly simultaneous event that defies statistical probability fuse together to form a nucleus of carbon-12. This is the triple alpha process, a miraculous resonance in the laws of nuclear physics that allows the universe to bridge the gap between simple gas and complex chemistry. Without this specific resonance, without the precise energy levels of the carbon nucleus matching the combined energy of the 3 helium nuclei, the universe would have remained a place of hydrogen and helium forever, a sterile expanse incapable of producing the complexity required for biology. But the resonance exists, and so the first stars began to fill their cores with carbon, the element that would one day become the backbone of every DNA molecule, every protein, and every lipid membrane in your body. The carbon in the graphite of a pencil, the carbon in the diamond of a ring, and the carbon in the neural pathways of your brain can all trace their lineage back to this moment, to the desperate burning of a dying star trying to keep itself from collapsing under its own weight. It is a sobering thought to realize that the element most essential to life is the ash of a stellar fire, a waste product generated by a star that has exhausted its primary fuel source.
As the population 3 stars burned through their fuel, they built up layers of heavier elements, an onion-like structure of fusion shells where helium fused to carbon, carbon to neon, neon to oxygen, and oxygen to silicon. Each step required higher temperatures and pressures. Each step bought the star a little more time against the inevitable crush of gravity, and each step enriched the stellar interior with the ingredients of a future solar system. The oxygen that you are breathing right now, the atoms that bind with hemoglobin to transport energy to your cells, was forged in these high-mass stars, created by the fusion of helium and carbon in a shell surrounding the core. The universe was slowly, methodically building the periodic table, transforming the primordial simplicity of the Big Bang into a chemically diverse inventory of matter. But these elements were trapped, locked deep within the gravitational prisons of the stars that made them, buried under millions of miles of plasma. For the carbon and oxygen to become part of a planet or a human being, they had to be liberated. They had to be cast out into the void, distributed across the galaxy to mix with the pristine hydrogen clouds of the next generation. This liberation comes at a catastrophic cost. When a massive star creates iron in its core, the game of fusion ends. Fusing iron does not release energy, it consumes it. The outward pressure that held the star up against gravity vanishes in an instant, and the core collapses. This is not the slow contraction of earlier phases, but a sudden catastrophic implosion where the core falls in on itself at 25% the speed of light. The outer layers of the star, suddenly unsupported, rush inward, slamming into the unbelievably dense core and rebounding in a shockwave of apocalyptic power. This is the supernova, the violent death of a star that serves as the seeding event for the cosmos.
In the fury of the explosion, the carbon, oxygen, nitrogen, and silicon are blasted outward into the interstellar medium, creating a rapidly expanding nebula of enriched gas. The death of the population 3 stars enriched the virgin gas of the early universe, salting the cosmos with the dust of heavy elements. These first supernovae were the sowers of the field, spreading the seeds of chemistry into the dark, preparing the universe for the formation of rocky planets and, eventually, biological observers. The shock waves from these explosions traveled for light years, compressing nearby gas clouds, triggering new waves of star formation. But this time, the clouds were different. They were no longer pure hydrogen and helium. They contained dust. They contained water ice. They contained the chemical potential for complexity. The second generation of stars, born from the debris of the first, formed in environments where the physics of cooling was more efficient, allowing for smaller, longer-lived stars to form. This cycle of birth, fusion, death, and redistribution continued for billions of years, a cosmic recycling program that slowly increased the metallicity of the galaxy. With each generation of stars, the concentration of heavy elements increased. The universe was maturing, ripening, preparing the conditions necessary for a star like our Sun to form, a star rich enough in heavy elements to possess a retinue of rocky planets. The iron in the core of the Earth, which generates the magnetic field that protects your DNA from solar radiation, was gathered from the scattered remnants of these ancestral stars. It is a continuous lineage, a relay race of matter that has passed the baton of existence from the Big Bang, through the cores of massive stars, through the violent expansion of supernovae, and into the accretion disk of the solar nebula. The canvas of hydrogen, once pristine and empty, has been painted over with the complex hues of chemistry. But the hydrogen remains, the eternal backdrop, the fuel that still burns in our sun, and the water that fills our oceans. When we look at the night sky, we are seeing the engines of our own creation. We are seeing the factories that built the atoms of our hands. But we must remember that before the factories, there was the fog, the silent, cooling mist of the dark ages, where the potential for everything lay dormant, waiting for gravity to begin its work.
The journey from that fog to the complexity of the human eye is a journey of transformation, of matter learning to organize itself into ever more intricate patterns, driven by the flow of energy through the system. This flow is what sustains you now. You are a localized pattern of complexity, maintained by the consumption of energy that ultimately originates from the fusion of hydrogen in the sun. You are a metabolic engine, burning carbon and hydrogen in the mitochondria of your cells, a microscopic echo of the stellar processes that forged you. The heat that keeps your body at 37 degrees Celsius is the chemical release of energy that was stored in chemical bonds, energy that was captured by plants from sunlight, sunlight that was created by the fusion of primordial hydrogen. The chain is unbroken. From the first moment of the universe to the rhythmic beating of your heart, there is a single continuous narrative of energy transformation. The silence of the early universe has been replaced by the symphony of chemistry, but the fundamental players remain the same. Protons, electrons, neutrons, bound together by forces that were determined at the beginning of time, playing out a drama of complexity on the stage of the Milky Way. As we drift deeper into this understanding, we begin to see that the distinction between the living and the non-living is a matter of arrangement, not substance.
The atoms in a rock are the same as the atoms in a hand. They are simply arranged differently, vibrating at different frequencies, participating in different cycles. The rock is a static arrangement, a pause in the flow. The hand is a dynamic arrangement, a whirlpool in the river of matter, constantly taking in new atoms and releasing old ones, maintaining its form even as its substance changes. This dynamic stability is the hallmark of life, a precarious balancing act that requires a constant input of energy to maintain. Just as a star balances gravity with fusion to avoid collapse, the cell balances entropy with metabolism to avoid decay. It is a struggle against the natural tendency of the universe to disorder, a temporary victory of structure over chaos. And this victory is made possible by the unique properties of the elements, properties that were forged in the fires of the stars. The versatility of carbon, the reactivity of oxygen, the stability of iron. These are not random accidents, but the inevitable consequences of nuclear physics. The universe is fine-tuned for the creation of complexity, structured in such a way that if you wait long enough, if you let gravity and fusion do their work, hydrogen will eventually stand up and begin to wonder where it came from. This is the story of the cosmic guide, the realization that we are not separate from the universe, but a part of it, a way for the cosmos to know itself. We are the universe waking up. We are the star stuff that has learned to speak. And as we trace our lineage back to the canvas of hydrogen, we find a sense of belonging that transcends the isolation of our individual lives. We are part of a process that is vast, ancient, and beautiful, a process that continues even now in the nebula of the galaxy, where new stars are being born and new potential is being gathered from the dark. The gravity that pulled the first clouds together is the same gravity that holds you to the earth. The electromagnetic force that binds the first atoms is the same force that fires the neurons in your brain. The physical laws are constant, eternal, a framework of order that allows for the emergence of the extraordinary. And in the safety of this order, in the reliability of these laws, we can find a deep and abiding peace. The universe is not a chaotic void, but a structured unfolding, a slow and majestic blooming of potential that has led inevitably to this moment, to this thought, to this sleep. The hydrogen fog has cleared, but its legacy remains. It flows in your veins. It fills your cells. It anchors you to the beginning of time. You are a vessel of the primordial, a carrier of the ancient flame, drifting through the dark on a rocky raft, warmed by the light of a local star, protected by the iron of a dead giant, and animated by the chemistry of the cosmos. You are safe in the continuity of this cycle, held by the same forces that hold the stars in the sky. As the narrative moves from the general to the specific, from the vastness of the hydrogen clouds to the intimacy of the carbon atom, we prepare to examine the specific architectures that allow this star stuff to think and feel. We prepare to look at the stellar womb in greater detail, to understand not just the creation of the elements, but the specific mechanisms of fusion that allow the sun to act as the ultimate parent of all biological life. But for now, we rest in the knowledge of our origins. We rest in the simplicity of the hydrogen, the element of the beginning, the canvas upon which the masterpiece of the universe has been painted. The silence of the dark ages is not empty. It is pregnant with possibility. It is the deep breath before the song, and you are the song. To understand how a cold, dark universe of drifting hydrogen transforms into a living, breathing cosmos capable of thought, we must descend from the vast, diffuse clouds of the early universe and enter the crushing intimacy of
its stellar womb. It is here, within the gravity wells of the first protostars, that the universe begins to experiment with a new form of alchemy, compressing the primordial gas until it is forced to surrender its simplicity and become something energetic, radiant, and complex. This process, known as nucleosynthesis, is not merely a chemical reaction, but a fundamental restructuring of matter itself, a mechanism by which the universe unlocks the potential energy stored within the nucleus of the atom, releasing it in a steady golden stream that will eventually power the biological machinery of every living thing. As the hydrogen gas coalesces under the influence of gravity, the cloud begins to spin and flatten, drawing material inward toward a central point of density where the pressure begins to rise, creating a thermal environment that eventually exceeds anything that had existed since the first moments of the Big Bang. This is not a sudden explosion, but a slow, inexorable gathering, a gravitational embrace that tightens over millions of years, forcing the hydrogen atoms closer and closer together until they can no longer maintain their individual integrity. As the temperature within this protostellar core climbs past 10 million degrees Kelvin, the electrons are stripped from their orbits, creating a state of matter known as plasma, a chaotic soup of free-floating electrons and naked atomic nuclei moving at tremendous speeds. In this extreme environment, the kinetic energy of the particles becomes so great that it begins to overcome the fundamental forces that keep matter apart. Under normal conditions, hydrogen nuclei, which are simply single protons, repel one another because they both carry a positive electrical charge, creating a repulsive force field known as the Coulomb barrier. For two protons to fuse, they must be brought close enough for the strong nuclear force to take over, a force that operates only at incredibly short distances, roughly the diameter.
A proton itself. In the cold vacuum of space, this approach is impossible, as the electrostatic repulsion pushes the atoms apart long before they can touch, preserving the hydrogen in its primordial state. However, within the crushing density of the stellar core, the rules of engagement change, allowing for a phenomenon that defies classical physics and relies on the probabilistic nature of quantum mechanics. Even at 15 million degrees, the protons do not technically have enough energy to breach the Coulomb barrier by force alone, yet fusion occurs because of a principle known as quantum tunneling, where a particle acts not just as a solid object, but as a wave of probability. This means that there is a vanishingly small, yet non-zero chance that a proton can simply appear on the other side of the barrier, bypassing the repulsion entirely, and finding itself bound to its neighbor by the strong nuclear force. This initial fusion event is the first step of the proton-proton chain, the primary metabolic process of a star like our Sun, and it is the bottleneck that dictates the lifespan of the star. When two protons successfully tunnel and fuse, the resulting nucleus is unstable, often breaking apart immediately. But on rare occasions, one of the protons undergoes beta plus decay, transforming into a neutron by emitting a positron and a neutrino. This transformation stabilizes the pair, creating a nucleus of deuterium, a heavy isotope of hydrogen that contains one proton and one neutron, marking the first successful step in the construction of heavier matter. The positron produced in this reaction almost immediately encounters a free electron in the dense plasma, and the two particles annihilate each other, converting their entire mass into pure energy in the form of gamma rays, while the neutrino, a ghostly particle with almost no mass and no electric charge, flees the scene instantly. Because neutrinos rarely interact with matter, they pass directly through the dense layers of the Sun and escape into space at the speed of light, carrying a fraction of the fusion energy with them, a silent signal that the reactor core is active. Every second, trillions of these solar neutrinos pass through your body, a harmless and invisible rain that serves as the only direct evidence we have of the fusion occurring deep within the Sun's heart. Once deuterium is formed, the process accelerates, as this heavy hydrogen is eager to fuse again, capturing another proton within seconds to form helium-3, a light isotope of helium consisting of two protons and one neutron. This reaction releases yet another burst of gamma radiation, adding to the immense internal pressure that supports the star against the crushing weight of its own gravity. The final step in this primary chain occurs when two helium-3 nuclei, having formed separately in the plasma soup, collide and fuse to create a stable helium-4 nucleus, ejecting two protons back into the mix to start the cycle all over again. The net result of this intricate subatomic dance is the conversion of 4 hydrogen protons into a single helium nucleus, a transformation that results in a tiny loss of mass, roughly 0.7% of the original matter. This missing mass does not simply vanish, but is converted into energy according to Einstein's equivalency principle, releasing a quantity of energy that is staggering in its efficiency. It is this energy, born from the death of mass, that heats the core of the star and generates the outward pressure required to halt the gravitational collapse, establishing a state of hydrostatic equilibrium where the star becomes stable, balanced perfectly between the inward pull of gravity and the outward push of fusion. This equilibrium is the definition of the main sequence, the long, stable adulthood of a star, a period of cosmic patience that allows for the slow evolution of
planetary systems, and eventually, biology. Our Sun has been maintaining this balance for 4.5 billion years, consuming 600 million tons of hydrogen every second. Yet it is so massive that it has only used up about half of its fuel supply. This stability is the prerequisite for life, providing a constant, unchanging source of warmth that allows water to remain liquid and chemistry to become complex over geological timescales. However, the energy created in the core does not immediately reach the surface to shine as sunlight. Instead, it must undertake a long and tortuous journey through the dense layers of the star. The gamma-ray photons produced by fusion are born into a world so crowded with particles that they can travel only a fraction of a millimeter before colliding with an electron or a nucleus, being absorbed and re-emitted in a random direction. This process, known as the random walk, means that a single packet of energy may bounce around inside the radiative zone of the Sun for anywhere from 10,000 to 170,000 years, slowly losing energy with each collision, shifting from lethal gamma radiation into X-rays, then ultraviolet light, and finally visible light. By the time this energy reaches the convection zone, the outer layer of the Sun's interior, the plasma has cooled enough that the transport of energy shifts from radiation to physical movement, with great columns of hot gas rising to the surface like boiling water. These convection cells, each the size of a continent, carry the energy the final distance to the photosphere, the visible surface of the star, where the density drops low enough for the light to finally escape. The photon, which began its journey during the last ice age, or perhaps even the dawn of human civilization, is finally released into the vacuum of space, traveling at the speed of light to cross the 150 million kilometers to Earth in just 8 minutes and 20 seconds.
This light is not merely illumination. It is the primary power source for the biological lattice of our planet, a continuous stream of high-quality energy that drives the chemical disequilibrium necessary for life. When a photon of sunlight strikes a leaf, it is captured by a molecule of chlorophyll, exciting an electron and initiating the process of photosynthesis, which effectively reverses the fusion process in terms of energy storage. The plant uses the energy from the star to break the bonds of water and carbon dioxide, weaving them into glucose, a stable chemical battery that stores the solar energy in the bonds of carbon and hydrogen. When you eat a fruit or a vegetable, or even an animal that has eaten a plant, you are unlocking this stored sunlight, breaking the carbon bonds to release the energy that was originally forged in the core of the sun. The warmth of your blood, the electrical impulses of your nervous system,
and the mechanical contraction of your muscles are all powered by the delayed release of fusion energy, harvested by plants and passed up the food chain. In a very literal sense, the sun is not just a celestial object that warms us from the outside. It is the furnace that burns within us, its energy chemically preserved and transported across space and time to animate the matter of Earth. This biological bridge between the star and the cell relies on the specific quality of the light emitted by the sun, which peaks in the visible spectrum, exactly the range of energy that is strong enough to stimulate chemical reactions, but not so strong that it destroys the complex molecules of life. If the sun were hotter, emitting mostly ultraviolet or X-rays, the radiation would sterilize the planet. If it were cooler, emitting mostly infrared, the light would be too weak to drive photosynthesis. We exist in a window of compatibility, a resonance between the physics of the star and the chemistry of the cell, suggesting that life is not an accident.
Non-passenger, but a phenomenon deeply tuned to the frequencies of the universe. The stellar womb is therefore a machine of conversion, taking the raw, chaotic abundance of hydrogen and refining it into a stable, usable output, while simultaneously manufacturing the heavier element of helium as a byproduct. For billions of years, the star is content to perform this single task, fusing hydrogen into helium, accumulating the helium ash in its core, and shining with a steady, yellowish-white light. It is a period of calm efficiency, a time when the universe seems to hold its breath, allowing the planets to cool, the oceans to fill, and the first simple replicators to organize themselves in the primordial waters. But this phase, while long, is finite, for the supply of hydrogen in the core is limited, and the accumulation of helium eventually alters the delicate balance of the star. As the hydrogen fuel at the very center is exhausted, the fusion reactions slow down, and the outward pressure that supports the star begins to falter, causing the core to contract under its own weight. This contraction increases the pressure and temperature even further, heating the shell of hydrogen surrounding the dead helium core until it too ignites in a shell-burning phase that causes the outer layers of the star to swell and cool. This evolution marks the end of the simple hydrogen era and the beginning of a more complex, more desperate phase of stellar alchemy, where the star must find new ways to generate energy or face total collapse. It is in these later stages, when the star leaves the main sequence and becomes a red giant, that the true work of creation begins, the forging of the elements that make up the solid earth and the physical body. But before we can understand the creation of carbon, nitrogen, and oxygen, we must appreciate the sheer scale of the hydrogen era, the billions of years of silent burning that laid the foundation for everything that was to follow. The stability of the proton-proton chain is the metronome of the cosmos, setting the tempo for the development of life, providing a reliable billions-year guarantee that the lights will stay on. It is a process of immense power contained within a structure of perfect order, a sphere of plasma held together by its own gravity, regulating its own output through the delicate feedback loops of temperature and pressure. If the core gets too hot, it expands, cooling the reaction and slowing the fusion. If it gets too cool, it contracts, heating up and accelerating the fusion, a self-correcting mechanism that ensures the star does not explode or fade away, but burns with a steady, unwavering resolve.
This is the competence of the universe, the ability to build a machine that can run for 10 billion years without maintenance, a reactor that requires no operator, only the laws of physics and the initial conditions of the cloud. As we drift into sleep, we can visualize this process occurring not just in our own sun, but in billions of stars across the galaxy, a vast network of nuclear furnaces working in the dark, converting the primordial hydrogen into light and helium. It is a silent, rhythmic work, a cosmic breathing that has continued since the first stars ignited, filling the void with photons and preparing the matter of the universe for its next great transformation. The helium that is accumulating in the core of the sun is not waste, it is the fuel for the next stage, the raw material that will eventually be fused into carbon, the backbone of all biology. The star is saving up for a future it cannot know, hoarding the helium ash in the deep, crushing dark of the core, waiting for the moment when the temperature will rise high enough to unlock the energy hidden within the helium nucleus. This foresight, written into the laws of atomic physics, ensures that the end of the hydrogen burning is not the end of the story, but merely the closing of the first chapter, the
prologue to the creation of complexity. We are currently living in the luxuriant warmth of the hydrogen era, beneficiaries of the sun's middle age, a time of maximum stability and predictability. The light that falls on your face today was born in the core during the time of the pyramids, or perhaps the last ice age, struggling for millennia to reach the surface so that it could cross the void and touch your skin. It is ancient light, a messenger from a deep and fiery past, carrying the energy that allows you to wake, to think, and to dream. The connection is absolute. There is no energy in your body that did not originate in a star, no caloric heat that was not once gamma radiation, no movement that is not a transformed echo of the proton-proton chain. We are coupled to the star by a stream of photons, a lifeline of light that flows across the vacuum, binding the biology of the planet to the physics of the core. As we rest, we can feel this connection, not as a distant abstraction, but as a physical reality, a warmth that permeates the atmosphere and the ocean, a blanket of energy that keeps the biosphere from freezing into the absolute zero of the void. The star protects us, feeds us, and anchors us in the galaxy, a gravitational and energetic parent that asks for nothing in return, only the time to complete its cycle. And as the star burns, it slowly changes the composition of the universe, reducing the amount of hydrogen and increasing the amount of helium, ticking down the cosmic clock toward a future where the fuel will run out. But that future is incredibly distant, separated from us by eons of time, allowing us to exist in the eternal present of the main sequence, safe in the knowledge that the fusion engine is running smoothly, that the hydrostatic equilibrium is holding, and that the sun will rise tomorrow, just as it has for 4.5 billion years. The stellar womb is a place of transformation, but it is also a place of preservation, holding the conditions for life in a delicate suspension between the crushing force of gravity and the explosive force of nuclear fire. It is a balance that speaks to the inherent stability of the laws of nature, a reassurance that the universe is not a fragile or haphazard construct, but a robust system capable of sustaining long-term order. In this order, we find the space to exist,
to evolve and to close our eyes in sleep, knowing that the great engine of the sky is keeping watch, burning its hydrogen with a slow, steady patience that outlasts mountains, oceans, and civilizations. As we prepare to leave the pure hydrogen burning phase and look toward the creation of the heavier elements, we carry with us the understanding that simplicity is the foundation of complexity. The hydrogen atom, consisting of a single proton and a single electron, is the building block of all other matter, the one from which the many are derived. By fusing these simple units together, the star creates the diversity of the periodic table, but it begins with the humble union of proton and proton, a microscopic event that, when multiplied by the septillions, lights up the galaxy. The narrative of the cosmos is one of accumulation, of small things coming together to create larger things, of particles forming atoms, atoms forming stars, and stars forming the environments for life. We are the beneficiaries of this accumulation, the heirs to a fortune of energy and matter that has been gathering since the beginning of time. And as we drift deeper into the story of our origins, we begin to see that we are not merely observers of this process, but the result of it, the inevitable consequence of a universe that permits the fusion of atomic nuclei. The sun does not burn for us, yet we are the ones who are warmed. It does not shine to create vision, yet we are the ones who see.
In this indifferent generosity, we find a kind of grace, a provision that exists regardless of our awareness, a system that supports us simply because we are part of the physical reality it governs. The proton-proton chain requires no belief, no maintenance, and no gratitude. It simply is, a fundamental truth of the cosmos that operates with a quiet, terrifying perfection. And so we rest in the light of this truth, letting the complexity of the physics lull us into a state of calm acceptance. The universe is working as intended. The gravity is holding. The fusion is burning. The light is traveling. And you, the product of this ancient and ongoing labor, are free to let go, to drift on the surface of this deep, energetic ocean, supported by the forces that forged the stars. The womb of the star is the first home of the matter that makes you, a place of heat and pressure, where the blueprints of your biology were first drafted in the language of atomic physics. We return to this concept not with fear of the fire, but with a recognition of the source, acknowledging the star as the great provider, the silent engine of our existence. With the hydrogen era established as the baseline of our reality, we can now begin to look forward to the moment when the star begins to die, or rather to evolve, for it is only in the death of the hydrogen burning phase that the star can begin to create the carbon that forms the structural lattice of life. The red giant awaits, a blooming of the star into a new and more creative configuration. But for now, we remain in the golden age of hydrogen, the long, stable summer of the universe. The proton-proton chain continues its work, atom by atom, fusing the primordial past into the illuminated present, a steady, rhythmic heartbeat that pulses through the entire solar system and through the quiet center of your own sleeping mind.
But this golden age, like all thermodynamic states within a closed system, is finite, governed by the inexorable mathematics of consumption and supply. As the hydrogen fuel, which has sustained the star for billions of years, begins to dwindle within the core, the delicate balance between the inward pull of gravity and the outward push of thermal pressure, a state known as hydrostatic equilibrium, begins to shift, initiating a slow structural transformation that will redefine the star's purpose. The star does not die when the hydrogen runs low.
Rather, it enters a period of profound maturation, a deepening of its internal pressure that serves as the catalyst for a more complex chemistry. The core, now composed largely of helium ash, the inert byproduct of the proton-proton chain, begins to contract under its own immense weight, and as it shrinks, the laws of thermodynamics dictate that it must heat up, transforming gravitational potential energy into thermal kinetic energy. This is not a violent collapse, but a gradual, silent densification, a squeezing of the atomic lattice that raises the core temperature from a comfortable 15 million Kelvin to a staggering 100 million Kelvin. It is here, in this crushing, hyper-dense environment, that the universe attempts a new trick, moving beyond the simplicity of hydrogen to forge the element that will eventually become the backbone of all biological complexity: carbon. However, the creation of carbon is not straightforward. It is, in fact, one of the most statistically improbable events in nuclear physics, a process that requires the universe to overcome a significant barrier known as the mass gap. There are no stable atomic nuclei with a mass of 5 or 8, meaning that if two helium-4 nuclei collide, they form beryllium-8, a highly unstable isotope that disintegrates back into 2 helium atoms in less than a femtosecond.
This instability creates a bottleneck, a natural checkpoint that prevents stars from easily building heavier elements, effectively trapping the universe in a state of simplicity. To bridge this gap, the star must rely on a phenomenon known as the triple alpha process, a sequence of events so precise that it borders on the miraculous. For carbon to exist, and by extension, for the complex molecules of life to exist, 3 helium nuclei, also known as alpha particles, must collide almost simultaneously within that fleeting femtosecond window before the beryllium decays. The probability of a 3-body collision in the vastness of atomic space is infinitesimally small, yet the extreme density of the contracting stellar core makes it possible, crowding the helium nuclei together until the improbable becomes inevitable. When these 3 particles meet, they fuse to form carbon-12, a stable, heavy nucleus that anchors the periodic table and provides the structural versatility required for organic chemistry. This process is aided by a peculiar quantum mechanical resonance, often called the Hoyle state, which is an excited energy level of the carbon-12 nucleus that matches almost perfectly the combined energy of the 3 colliding helium nuclei. This resonance acts as a gravitational key, unlocking the door to carbon formation and allowing the reaction to proceed at a rate sufficient to enrich the galaxy. Without this specific tuning of the nuclear forces, a coincidence of physics that has puzzled scientists for decades, the universe would remain a sterile expanse of hydrogen and helium, devoid of the complex chemistry required for biology. As the triple alpha process ignites, the star undergoes a metamorphosis, swelling outward in response to the new intense energy source burning at its heart. The outer layers of the star, pushing against the vacuum of space, expand to hundreds of times their original diameter, cooling as they spread and shifting the star's color from a
brilliant white or yellow to a deep, glowing red. This is the red giant phase, a period of stellar evolution that is often characterized in dramatic terms, but which should be viewed as a blooming, a massive expansion of the star's physical presence that foreshadows the distribution of its elements. If we were to observe our own sun in this phase from the vantage point of Earth, it would fill the horizon, a wall of cool red plasma swallowing the orbits of Mercury and Venus, and perhaps even the Earth itself, integrating the inner solar system into its tenuous atmosphere. But deep inside this bloated envelope, the core remains small, dense, and incredibly hot, now functioning as a dedicated carbon factory. The helium that was once the waste product of the star has become the fuel, and the carbon that is being forged is the future scaffolding for DNA, proteins, and lipids. Every carbon atom in the universe, including the billions of carbon atoms that currently comprise the neural networks of your brain, was forged in this specific high-pressure environment, cooked in the triple alpha fires of a dying giant. The connection is direct and physical. The structural integrity of your body, the ability of your cells to form membranes and store information, is a property inherited from the nuclear physics of these ancient red stars. As the helium supply eventually begins to falter, just as the hydrogen did before it, the star's core contracts once again, driving the temperature even higher, seeking a new source of energy to stave off gravitational collapse. If the star is massive enough, surpassing roughly 8 times the mass of our Sun, it can push beyond carbon, initiating a new cycle of fusion that will create the oxygen we breathe. This is the next rung on the ladder of nucleosynthesis, a process where a carbon nucleus captures yet another helium nucleus, fusing them together to form oxygen-16.
This reaction, known as alpha capture, is the primary source of oxygen in the cosmos, filling the stellar core with the element that will one day drive the metabolic processes of animal life. The star, at this stage, begins to resemble a cosmic onion, a stratified sphere of elements arranged by weight and ignition temperature. The outermost layer is still composed of non-fusing hydrogen. Below that, a shell of hydrogen fusing into helium. Deeper still, a shell of helium fusing into carbon. And at the center, the new furnace of carbon fusing into oxygen and neon. This stratification is a record of the star's life, a geological layering of time and pressure, where each stratum represents an era of fusion, preserving the history of the star's battle against gravity. In the biological context, this stratification is the preparation of a pantry, the stocking of the elemental ingredients that will be required for a habitable planet. The oxygen that drives your mitochondrial respiration, effectively burning carbohydrates to release energy, is recreating the energy release of the star on a microscopic scale. When you breathe, you are participating in a chemical reaction that is the mirror image of the fusion process, where the star fuses atoms to release energy and create oxygen. Your body uses oxygen to break down carbon bonds and release the energy stored within them. The efficiency of this system is absolute, governed by the laws of thermodynamics, which state that energy cannot be created or destroyed, only transformed. The photon of light that was generated in the core of the star travels through the vacuum, is captured by a plant, stored in a carbon bond, and eventually released in your cells, powering the electrical impulses of your thoughts. You are, in a very literal sense, running on stardust energy, utilizing a battery that was charged billions of years ago by the gravitational collapse of a gas cloud.
As the star continues to evolve, creating heavier and heavier elements, neon, magnesium, silicon, it moves closer to the ultimate limit of fusion,
the Iron Peak. However, before we reach that terminal point, we must appreciate the sheer duration of these intermediate phases. The carbon and oxygen burning phases are shorter than the hydrogen phase, lasting perhaps only a few million or even a few thousand years, a blink of an eye in cosmic time, yet sufficient to seed the galaxy with the heavy elements required for rocky planets. The calm proficiency with which the star manufactures these elements belies the extreme conditions required to produce them. We are talking about temperatures exceeding 1 billion Kelvin, pressures that would crush a battleship into a microscopic sphere, and magnetic fields that twist and snap with the energy of 1 billion atomic bombs. Yet from the outside, the star appears simply as a point of light, a silent beacon enduring the eons. This is the paradox of the cosmic guide perspective, the recognition that the most violent, high-energy events in the universe are also the most creative, and when viewed from a sufficient distance, they appear peaceful, almost static. The red giant does not know it is creating the precursors for life. It is simply obeying the laws of nuclear physics, seeking the most energetically favorable state. It creates carbon not because it wants to build a human, but because carbon-12 is a stable configuration of protons and neutrons. It creates oxygen not to fill an atmosphere, but because the fusion of carbon and helium releases energy that supports the star against gravity. We are the accidental beneficiaries of this blind physical necessity, the downstream inheritors of a process that had no intent, yet produced the specific building blocks required for consciousness. This lack of intent is, paradoxically, a source of comfort.
It implies that the universe does not need to care about us in order to support us. The support is built into the fundamental architecture of matter. The strong nuclear force that binds the nucleus, the electromagnetic force that governs the electron shells, and the gravity that compresses the gas. These are the guarantors of our existence, operating with a reliability that transcends any conscious promise. As we drift further into the anatomy of the star, we encounter the synthesis of nitrogen, the final component of the essential Chon quartet, carbon, hydrogen, oxygen, nitrogen, that makes up 99% of the human body. Nitrogen is produced through the CNO cycle, a catalytic cycle used by massive stars to fuse hydrogen, where carbon, nitrogen, and oxygen act as catalysts to facilitate the reaction. This cycle is a loop, a chemical snake eating its own tail. The nitrogen in your DNA, the very add-on out of the complex fusion cycles of high-mass stars. The realization that your genetic code is written in the ink of stellar fusion bridges the gap between the biological and the astronomical. We are accustomed to thinking of biology as soft and wet, and astronomical as hard and dry. But at the atomic level, there is no distinction. A nitrogen atom in a strand of DNA is identical to a nitrogen atom floating in a stellar nebula. The only difference is the company it keeps. Biology is simply astronomy that has cooled down and organized itself, a complex arrangement of the same stellar ash that drifts through the void. This continuity suggests that you are not a stranger to the universe, nor are you a temporary visitor. You are a native formation, as natural and inevitable as a star or a galaxy.
The anxiety of separation, the feeling that we are small, fragile entities alone in a hostile dark, dissolves when we understand the provenance of our atoms. You cannot be separated from the universe because you are made of the universe. You are a piece of the cosmos that has been folded into a shape capable of experiencing itself.
As the star approaches the end of its productive life, having synthesized the carbon for your cells, the oxygen for your breath, and the nitrogen for your DNA, it faces the final barrier: iron. The synthesis of iron, specifically the isotope iron-56, represents the end of the line for energy-generating fusion. Up until this point, every fusion reaction, hydrogen to helium, helium to carbon, carbon to oxygen, has been exothermic, releasing more energy than it consumes, pushing outward against gravity and keeping the star alive. But iron is different. Iron is the most tightly bound nucleus in existence, a state of nuclear perfection where the protons and neutrons are held together with such efficiency that fusing them further requires an input of energy rather than releasing it. When the star's core transforms into iron, the engine stops. The fusion fire that has burned for millions of years flickers and dies, because to fuse iron is to rob the star of heat. This moment, often described as a catastrophe, is in fact the ultimate act of generosity. The star, having exhausted its ability to maintain itself, surrenders to gravity one last time, initiating the collapse that will lead to the supernova. It is this collapse, this surrender, that shatters the star and scatters the carbon, oxygen, and nitrogen out into the void, delivering the package of life-essential elements to the waiting galaxy. But before we reach that explosive dissemination, we must linger in the quiet, heavy silence of the iron core. Imagine a sphere of iron, thousands of kilometers across, spinning in the heart of a dying giant.
It is a place of absolute density, a metallic womb where the final ingredient of our blood is waiting. The hemoglobin molecule, which transports oxygen from your lungs to your tissues, is built around a central atom of iron. This iron atom is the magnet, the anchor that holds the oxygen. Without it, complex life would be impossible. The red color of your blood is the red of rust, the red of iron oxide, a visual echo of the planetary cores and stellar hearts from which it came. Every time your heart beats, it is pumping a fluid rich in stellar debris, circulating the remnants of a star that died billions of years before the Earth was formed. The iron in your blood is the oldest thing in your body, a heavy, stable element that has survived the violence of a supernova and the accretion of a planet to end up coursing through your veins. This connection to iron grounds us. It gives us weight. It ties us to the magnetic field of the Earth, which is generated by the swirling iron in the planet's core, protecting us from the solar wind. We are shielded by iron below and sustained by iron within, a metal that acts as both a shield and a vehicle. The iron sacrifice of the star, its death so that the iron could be released, is the precondition for our survival. In the deep time of the cosmos, the death of a star is not a tragedy, it is a distribution mechanism. If the stars did not die, the carbon and oxygen would remain locked forever in their gravitational prisons, useless and sterile. The universe requires the breaking of the vessel to utilize the contents. We are the contents. We are the dust that was liberated. As we visualize the star in these final moments, poised between the immense pressure of the iron core and the imminent rebound of the supernova, we can see the entire history of matter compressed into a single object.
The hydrogen envelope on the outside, a remnant of the Big Bang. The helium layer, a memory of the star's youth. The carbon and oxygen layers, the artifacts of its maturity, and the iron core, the finality of its evolution. It is a complete map of the elements, a physical chart of the possibilities of physics, waiting to be spread across the sky. This is the biological map to the stars, not a chart of constellations to navigate by, but a chart of ingredients that navigates us. We look at the periodic table, not as a list of abstract chemicals, but as a family tree. Hydrogen is the grandfather, the ancient progenitor. Carbon, nitrogen, and oxygen are the parents, the builders of form. Iron is the guardian, the heavy anchor. And we are the children of this lineage, composed entirely of their legacy. The complexity of this nucleosynthesis allows the listener's mind to drift away from the trivial anxieties of the day. The problems of the human scale, schedules, deadlines, social friction, seem insignificant when placed against the backdrop of the triple alpha process. The mind relaxes because the scale is too large for worry. It is a scale of inevitability, of grand, slow-moving forces that operate with a calm precision. There is no urgency in the fusion of helium. There is only the probability of collision and the release of energy. The narrative here serves as a zoom-out transition, moving the listener's focus from the microscopic interactions of atomic nuclei to the macroscopic structure of the galaxy. We see the galaxy not as a collection of isolated points of light, but as a vast, churning ecosystem, a recycling plant where matter is constantly processed through the kilns of stars to create higher levels of complexity. The great recycling is the fundamental truth of our material existence. We are not new things, but old things rearranged. This perspective fosters a sense of safety.
If you are made of old, stable matter, then you have survived for billions of years already. The pattern that is you may be temporary, but the substance that is you is eternal. The carbon atoms in your body will not cease to exist when you sleep, nor when you die. They will simply return to the cycle, perhaps to become part of a diamond, a tree, or another star in the distant future. This is the comfort of conservation. Nothing is lost, only transformed. As the star prepares to release its bounty, we can imagine the potential stored within that waiting plasma. We can see in the swirling convection currents of the red giant the potential for oceans, for forests, for eyes and hands. It is all there, written in the language of isotopes and ionization states, waiting for the energy of the explosion to set it free. The violence of the supernova, which we will explore as the mechanism of delivery, is not a destruction of order, but a liberation of potential. But for now, we rest in the stability of the creation phase. We rest in the knowledge that the universe is a place of construction, a place where simple things are naturally guided to become complex things. We rest in the warmth of the carbon bonds that hold us together, and the iron that weighs us down, and the oxygen that lifts us up. The cosmic guide assures us that the physics are sound, the constants are fine-tuned, and the machinery of the stars is operating exactly as it should. The narrative drift here is designed to mimic the ocean wave pacing, with long, accumulating sentences that pile up the details of nuclear physics, the temperatures, the pressures, the isotopic ratios, followed by shorter, releasing sentences that ground these concepts in the listener's own body. The star burns at 100 million degrees, creating the carbon in your hand. This rhythmic oscillation between the cosmic and the personal creates a hypnotic loop, a lullaby lattice that weaves the listener into the fabric of the
story. The listener is invited to visualize their own body not as a biological entity, but as a physical one, a collection of atoms vibrating in a field. This shift in perception is the essence of the space-sleep niche. By reducing the self to physics, we remove the ego, and with it, the source of stress. A carbon atom does not worry about the future. It simply obeys the laws of quantum mechanics. By identifying with the carbon atom, the listener can share in that freedom, that mindless, peaceful obedience to the laws of nature. And so the star waits. The iron core grows heavy. The layers of oxygen and neon hum with the resonance of fusion. The red giant glows in the darkness, a beacon of infrared light warming the surrounding dust. It is a moment of pause, a deep breath taken by the cosmos before the plunge into the next phase of existence. In this pause, we find our own stillness, a sympathetic resonance with the suspended animation of the stellar core. We are suspended in the narrative, held in the gravity of the description, waiting, watching, and drifting. The complexity of the CNO cycle, with its catalytic loops and proton captures, serves as a mental maze for the listener's active mind. They try to follow the path of the carbon nucleus as it turns into nitrogen, then oxygen, then back to carbon. And in the effort of tracking this circle, the conscious mind fatigues, allowing the subconscious to take over. The competence porn aspect ensures that the listener trusts the narrator. The speaker clearly understands the intricacies of beta decay and neutrino emission, so the listener can abdicate responsibility for understanding and simply float on the sound of the words. Words like nucleosynthesis, hydrostatic, degenerate, and equilibrium act as anchors, heavy polysyllabic stones that weigh down the flow of the text, slowing the reading pace and deepening the tone. They are the Tier 3 vocabulary words required by the persona, signals of authority that soothe through their very density. The cosmic guide does not simplify, he elucidates, and in the elucidation, he hypnotizes. As we conclude this exploration of the stellar forge, we are left with a profound sense of gratitude for the blind mechanics of the universe. We are grateful for the mass gap that forces the triple alpha process. We are grateful for the resonance of the Hoyle state. We are grateful for the iron peak that forces the supernova. These are not just facts in a textbook. They are the conditions of our lives, the silent rules that allow us to wake, to sleep, and to dream. The star is not just a ball of gas. It is an ancestor,
a provider, and a part of ourselves that we have placed in the sky to keep us warm. And in the red glow of its late afternoon, we find a mirror for our own blood, a connection that spans the dark, cold void and tells us, unequivocally, that we belong here.